We are joined by Johnston from Bugs, USA. Uh, and he would be talking about introduction to data analysis, visualization, and general wrangling with Python, Pandas, and Jupyter notebooks. So over to you, Andy.
Thank you. Let's see, can I share screens? Okay, I'd like to start out by saying that one of the things that impresses me most about changes in the life sciences over the last 30 or 40 years, aside from just the technology, is the availability of the technology. The fact that, you know, you can do PCR equipment in middle and high school instead of 40 years ago when it would take, you know, you had to be at a major university to run a gel even, and it would take all night to do it. Another thing I've noticed is that there's a lot more data available now than there used to be, a huge amount of publicly available data, far more than anybody could handle, and usually way more than you can fit in an Excel spreadsheet. So one of the wonderful things I discovered a few years ago was something called Jupyter Notebooks and Python. Python is a programming language, but you can also use it interactively. There is a module called Pandas, which actually creates a data set, pretty much a complete database in a variable, and allows you to do all database features interactively. Picking out what you want, graphing what you want, doing analysis on what you want. It's been extended into visualization and machine learning. And it was always free. You could always download Python and Jupyter notebooks onto your computer. More recently, something called Anaconda appeared, which actually allows you to organize your Python, your notebooks, in your environments. And then Google came out with Google Colab. Let me bring you to Google Colab. If you just go and Google Colab, you'll get a welcome to Collaboratory. You click that,
Andy, I think you've become muted.
I was muted? Okay, how about now?
We got you.
Okay, everything in the Jupyter in this is already a Jupyter notebook. Do I need to admit people?
No, we'll do it.
Okay. Rather than describe it in detail, let me just get started here. Okay, here's a Jupyter notebook. This one is based on data that's been collected on the passenger list from the Titanic, of which most of you will have heard. It's a database that includes things like the names, the cabins, the genders, the ages of the passengers, along with the fares that they paid for their tickets. Also, whether or not they survived. It's not a complete list. This is actually a training set for machine learning, but it is large enough that you can get some idea of really, if you had to be on the Titanic, who you'd rather be. When you're in a Jupyter notebook, it's divided into cells. In any cell, you can put anything you like. Okay. If it is a code cell, then when you execute it, if you've typed anything you like, that's not going to work because that's not Python code. This command here, pylab inline, this does two things. It loads some very useful modules, which otherwise you would have to import by hand. And it also tells the notebook, anytime you generate an image, do it inside the notebook. Don't pop it up in some other application. To execute a cell, you can either click that button that says go, or you can hold down the shift key and hit enter. And it goes. The next is that extremely useful module Pandas that I mentioned. Okay, I'm importing it as PD so I don't have to keep typing the word pandas. I will note that Pandas was originally developed by a Wall Street quantitative analyst to deal with the huge amounts of information that people have to deal with on Wall Street. Since then, it's evolved and lots of specialized software has been developed that works with it, including quite a lot in biology. You can do quite a lot in genetics. You can, well, you will see in a few minutes. Okay, now I'm going to read in some data. This data is stored in GitHub. I don't have it stashed locally. But the pandas command read CSV will happily accept a URL and go out and find a comma-separated value file and read it in. This one is already set up to be used as a data set, so it shouldn't take too much massaging to make work. Okay, the head command by default means show me the first 5 lines, first 5 records. If I want to see something else, I put in a different number. If I just type in DF, it'll show me the first 5 and the last 5. It also will tell me how big it is. I have 712 rows, that's 712 data records, each one of which has 12 fields in it. For those of you who are familiar with databases, this should be pretty straightforward. If you're not, let me tell you that a database is a collection of records. You can think of each record as the row of a matrix. Each record is made up of fields. Those come down to the different columns of the matrix. This record is made up of the fields passenger ID, survived P-class, and so forth up to embarked. That 0 out there was actually generated by Pandas. It wasn't in the original data set. In any relational database, you have to have an index. You have to have some unique reference in each record that makes that record distinct. I could load 100 identical records with exactly the same data in each one of them, but Pandas would still go ahead and generate a unique index for each one so that I had some way of addressing each one in turn. Okay. Now I'm going to do this in pieces. I have here, DF is my whole data frame, by the way. That's why I called it DF. And if I just type DF, I get the whole data frame. If I type DF cabin, like that, it gives me all the values just for the cabin field. And here's where it gets interesting. If I say cabin equal equal, this is the logical equal, and give it a value, it's going to tell me for each record, is that actually the cabin number there? Now, this isn't terribly useful in itself because I've got 712 values here, and I'm hoping at least one of them says true. But I can take this expression which generates this long series of Boolean true-false values, and use that feed that directly into DF as a reference. So what I'm really doing is I'm feeding DF this entire string of false and I hope true values. And it pulls out all the records for which cabin actually is D36. This is called Boolean indexing. If you are interested in finding a particular value or particular set of values or particular set of records, you can construct a logical statement that such and such equals such and such. You can extend it, you can use logical and or. You can filter as fine as you want. And you then use that as a logical mask for your data. And you can see that cabin D36 had 3 people in it. Sorry, 2 people in it. They seem to be young women. This being the period that it was, they are both designated as Miss, so that we know they are young single women. Cabin D36. And they paid a reasonable but not too large fare. We also know they survived. For convenience, if I want to be pulling out that value, DF cabin equal D36 a lot of times, I can assign it to a variable. By the way, it may be clear. Clarity is always good. I can type it like this to make it clearer that I am creating the mask and I'm assigning it to the word mask. So now I just say DF mask and I get cabin D36 again. Few other things. If I want general information about my data frame, DF info. This tells me what my index is. The index is numeric. It goes from 0 to 711. I have 12 data columns. It tells you the type, D type of the data column. That's the data type. A database, like most programming languages, will usually make a distinction between different types of data. Integer data and float data does not automatically go together. When Pandas tells you that something is object data, it generally means a text string. You could assume that object means text. And if you look at this, it's a good idea to look at this right after you load a data frame, just as a sanity check. Okay, the passenger IDs. The passenger IDs, which were assigned originally in the data frame, which probably could be perfectly good indices, are numeric, and they're being picked up as numeric. Survived is either 1 or 0. Passenger class, first, second, third. Name is going to be text. Sex is going to be M or F. Age is going to be a float value. This data set actually doesn't boil it down to the year, it boils it down to a decimal year. So for instance, there we have records of children under 1 as 0.5 and 0.8 years old. The rest of these involve like number of siblings, a few other things. The fare is sometimes interesting. Again, as long as everything in a column looks like it's of the same type. If it's a whole bunch of digits and no decimal points, Pandas will assume it's an integer. If it's digits and decimal points, it'll assume it's float. If it's anything else, it'll call it object. If it sees something that seems to be contradictory, it may or may not complain. If it sees something it doesn't like, it may simply call it not a number. If it's decided that a column is numeric and finds something that doesn't look numeric or is blank, it'll often just call it NaN, not a number. And that's one of the things I'm going to check for here. Are there any null values in this data frame? If I just type df is null, okay.
Denny, someone is asking if they can have the link to the data on the GitHub.
Oh, I'm sorry, sure. If you go to, okay, I posted a Google Drive link on the Slack for workshops. If you go to that link, you can download these notebooks. If you just want the raw, I guess you just want the raw link to this. see, is chat a good place to put that?
Yes, hit them in.
There's chat.
I shared the drive you sent to the chat. If it's the same one, if
I'm
it's
sorry.
yeah, got it.
Okay. Yeah, this one is small enough to fit into an Excel spreadsheet if you want to play with it there. Okay, where are we? Okay. If I say df is null, it gives me a data frame full of Boolean values. If I say any, what I'm really asking it is, are any of these true? Are any of these false? Now, if any of them are true, okay, here we are. Passenger ID. Okay, I have no nulls in passenger ID, survival, passenger class, name, sex. I have some nulls in age. I have nulls in cabin, and I have nulls in embarked. Embarked just means where'd you get on, which I believe your choices are Cherbourg and Southampton. By the way, if I type all, okay, all is a way to say, given a series of logical values, are all of them true? But I really want to know, are any of them null? And the answer is yes, in some of these, some of them are. So that I thought, at this point, I know nothing about this data. I just loaded it. So really what I'm using this for is just to explore the data. I'm not trying to understand anything about the data. I'm not forming a hypothesis. I'm not drawing conclusions. I'm just looking at the data frame and the data and seeing what's set up. So I am now pulling out, remember, df age is null is going to be, df age is going to give me the age column. It's going to be true for everything in the age column that is null. And I'm saying, show me every record in the data frame for which the age column is null. And that's what it's giving me. I notice also that in most of these, the cabin is null as well. I also notice there's an embarkation queue I need to look up because I have no idea where they're getting on board. Okay, this tells me I have 146 rows. That's 146 null rows out of 712. Okay. If I were doing a scientific analysis, this would hurt me, losing 146 out of 712. I would be sad. But since I'm just playing around here, I will continue to play. Okay, group by. I'm now curious to see a little more specifically where these missing data points are. Who is missing? Who do we not have information for? So one of the things I'm wondering, because one of the things I'm suspicious of about the Titanic is the passenger class, the difference between first, second, and third class. So I'm going to do a group by. I'm going to take this and I'm going to tell it to group by passenger class and give me counts. And this is telling me that of the null records, 109 of them, 109 of the empty ones are in third class, 9 of them are in second, 28 are in first. That's certainly not totally in third class, but there seems to be a lot of missing data in third class. And it could be that this data simply didn't survive. It could be that these folks' cabins were never noted. For all I know, they may not have had cabins. I don't know what the setup was like on the Titanic. I haven't seen the movie, by the way. Okay, now I'm going to dig in a little further. I'm going to break it down by passenger class and who survived. Okay. First class passenger, again, this is just for the people with those with that null cabin data. Sorry, the null age data. And I see, okay, there's a tendency, it looks pretty even, it's evenly split, really, in first and second class. There's roughly a 2-to-1 bias in terms of having the non-survivors missing in third class. That's not too intense. But as I'm scanning this, my eyeball does note that just of these people, for first and second class, I've got about a 50% survival rate. And I have considerably less than that for third class. Okay. I'm just now going back to DF, here it is. DF mask, this is my original mask. Okay, and I believe if I haven't reassigned masks, these are my friends in cabin D36. Oop, nope, it's gotta be, oh, here it is. It's the age is null. Okay, these are the index values, the unique row values for which age is null. And they are presented in a special data construct called int64 index. And I'm now going to do some more jazzy stuff. I am going to tell the data frame to drop anything whose index value is in this list. And I'm going to tell it to do it in place. If I do in place equals true, sorry, false is where I want to start. In place equals false. Okay. What that means is don't change the original data frame. Just return the data frame with the changes I specified. So it returns a data frame with 566 rows, having dropped the ones here with null age. Because if I've decided just on a whimsy, if I don't have a good value for age in the record, I don't want the record at all. Now I'm going to do it again and say in place equals true. This time I don't get a return. Because in fact, instead of returning the changes that I wanted, it actually changed the data frame itself. So it's not feeding me back a new altered data frame, it actually changed the original. Now I use the shape attribute, and you see that my data frame is now 566 rows with 12 columns. Okay, I'm going to stop here briefly for questions if anybody has any. Okay.
Does anybody have?
Go ahead.
Use the chat. You can use the chat, or you can just ask and raise your hand. I'm taking this as a no. Okay, here's where we start getting into some of the powerful tools. This is called a pivot table. It's best described by I'm sorry, someone told you there's no math today? Wait till you see the next one. That's okay, it's harmless, it's good for you. Okay, what I've done here is I've said, okay, count some unique value, and the nice unique values are the passenger IDs. And index, which you can look at as the rows. In the rows, I want it broken out by survival. In the columns, I want it broken out by sex. Okay, this aggregation function, PD series and unique, for reasons I do not understand, Pandas does not recognize a function that simply says count. What PD series and unique does is it just says count the unique values. All right, so just take that, live with it. I'll show you how to fix it in the next cell. But here's my first breakout. I've counted up, broken out, male, female, survived, yes or no. Clearly, if you're going to be on the Titanic
you're probably better off being female, at least based on this data set. So women and children first. We don't know about children yet, but it looks like the women got into the boats disproportionately. Now, I mentioned that it's annoying that I don't have a function that simply says count. Python allows you to create a simple function on the fly using the command lambda. So what I'm telling it now is I want a function which, if I give it an x, I want it to give me back the count of x. We're assuming that x is a series of data. So now I can go back and do the same thing again. And you notice that a lot of what I'm doing here is not actually so much data driven as my own preference driven. One of the things I like about using Pandas and its associated modules in this notebook is I can start adjusting things to be more the way I like them. I can, once we get into graphing and plotting, you'll see I can pick my own colors. You know, you have tremendous amount of control over what you're doing. Okay, I'm going to look at a smaller subset of my data now. When you want to look at more than one column, for reasons we can go into later, you want to use double square brackets. Trust me on this for now. Okay, I just want to look at these data values: age, sex, fair, survived. So I'm going to create a mini data frame. There's my mini data frame. My mini data frame has just these 4 values in it. I'm going to say group by survived and sex and describe. And what it has done, it has taken, for instance, for survived female, these are the statistical descriptors of the ages and the statistical descriptors of the fairs. Specifically, for females who did not survive, there were 50. Their mean age was 27.28, standard deviation 13.5, minimum value 2, first quartile, median, third quartile, maximum value. Now, if this is statistical gibberish to you, don't worry about it. If in fact it is statistically interesting to you because you have to work with stats, just remember, it's just the describe function. The describe will immediately come right back at you with these descriptors. Okay, same thing for the fair. Mean fair was, I really don't know what this is in dollars or pounds. I'm going to assume pounds. 24.2 pounds sterling, which back then would have been serious money. Standard deviation, pretty high. And that makes sense because we go from 7 3/4 up to 151 pounds, which suggests there's a huge difference in passengers and how much they paid. Somehow, some of these men got on paying nothing at all. How that happened, I couldn't tell you. If you are interested in getting a PhD in history, there may be a dissertation floating in these numbers somewhere. Okay. Oh, by the way, I showed you how to look at all the cabins which had null values. If you want to look at the ones that don't have null values, this is the negation sign in Python. Okay, this is the one for cabin null not. Okay. Now, I'm going to get some graphics done. Pandas has its own built-in graphics, but there are better graphics, frankly, in the Seaborn module. And the Seaborn module is designed to take Pandas data frames. All right. I've told it I want figure size 2020, which may be a bit large for this screen, and I'm doing a scatter plot. In fact, I'm just going to shrink this a bit. That's better. Okay. This is a scatter plot. The horizontal axis is age. The vertical axis is the fair. Blue means they did not survive, and orange means they did. So we can just look at our data points here, and using our eyeballs, does this graph start to tell us anything right off the bat? And what I see is a big collection of blue right here at the bottom. Okay, across all ages, we have basically if you paid a low fare, you were almost certain to not make it. If you paid a higher fare, you might not make it, but up here, where the fares get higher, we get a lot of oranger, which seems suggestive. Okay, now, just in order to make the graph almost impossible to follow, because the fun thing about data is jamming too much into a graph so that no one can understand what you're doing, I have adjusted the shapes. It's the same graph as above, except if the dot is round, the passenger is male. If it's an X, the passenger is female. Now, at this point, I went into eyeball overload and couldn't see it anymore. My impression is that I've got a lot of blue males down here in the low fare. Going back to pivot tables. Okay, I get this. Now the problem here, I have not binned anything. I've told it for all the fares and for all the ages, I want to know who survived. Now, for most combinations of fare and age, there is no passenger there. Okay, there's no 0.42-year-olds who paid $0. There's a 19-year-old who paid $0, and that person survived. So this is like a whole lot of knotted numbers with a few ones scattered inside it for survival. But what I can do is take that same table, and instead of NaN, I'm going to put 0 in those values. Okay, fill value equals 0. That simply means if you don't have a number, call it 0. And then I'm going to take the whole thing, the whole tremendous mess, and put it into a heat map. There we go. Now in this heat map, I have all my ages increasing left to right. I have all my fares increasing from top to bottom. So I have to remember what I'm looking at. And there's only, since the only entries in here can be 1, the only values I can have here are 0, 1, 2, 3, and so forth. If there were, for instance, somehow 2 people who were 21 years old and paid £227,525, then it would show up as a 2. And I do have a few of those because this heat bar goes from 0 to 2. So what I'm really looking at is 0, 1, and 2. I will tell you something else historical about Pandas. Since it was created by a Wall Street quant analyst, it really likes to work in floating point numbers because most of the data you're getting, financial data, comes in as floating point numbers. It has been retrofitted to be kinder to integers, but it tends to just assume that what you really want is floating point. You can force the issue. Okay, I'm defining my own set of colors here. Black, gray, and white. I'm turning them into a color palette. I'm using that color palette on that same heat map, and that's better. Okay, this is a little bit easier on the eye. The sort of grayish dots mean there was a survivor there. The white dots mean there were 2 survivors there, and we don't go any higher. Another thing I see that may be good for someone's dissertation someday, you notice the age span tends to expand up here, for survivors at least, in that middle fair range, from about, call it 10 to 50. I don't know why. It could be no one else had kids. Who knows? This starts to suggest, though, I'm starting to find directions to dig in if I want to dig further into my data. This is really a methods demonstration. Okay, this is crosstab. Crosstab is essentially the same thing as pivot table, except it's happier to accept integers. That's not 1.0, it's just 1. Okay, and you get pretty much the same map, almost the same map using the crosstab, though here in some of these we're getting larger numbers.
And you've got about like 5 minutes.
Okay. In that case, I'm going to show you one more, just for the road. I hope this has been somewhat useful. I picked the Titanic one first because it pulled the data in directly off the net. And it was a good way to demonstrate wandering through a table of data about which you do nothing to start with. Okay, someone mentioned math. I want to just show off something else you can do. Some of you may be familiar with epidemiological models. Some of you, if you've done any writing in math or physics or even chemistry, may have run into LaTeX. LaTeX is a typesetting language for typesetting math. It doesn't do math, it just typesets math. But it means I can write stuff like this, okay, from a keyboard. I don't know how often any of you need to do that, but if you ever need to do this, I have used this when teaching math as a quick way to type up, nice, pretty equations, which I can then pass out to random students. There we go. Real quick, I've got 4 classes here. Wolfram Alpha is nice too. I find this a lot more convenient. Oh, you mean for generating LaTeX? Yes. Okay, I'm actually solving systems of ordinary differential equations here. You don't have to worry about that. But what this is you have an amount of the population at the start of an epidemic that's susceptible. Some of the susceptibles are going to be exposed. Some of the exposed will become infected over time. And one hopes that the infected will eventually be recovered and be immune. Okay, this is called the simple SEIR model. The assumption on how you get from one state to another is very simple. The more people there are who are susceptible, then in the next time step, the more people who will be exposed. The more people who are exposed in the next time step, the more people who will be infected. It all depends on the rate at which you move from one to another. Now, I set this one up to assume that some of these might change over time. I made the equation more complicated. I made it possible to go, for instance, from an immunized state to a susceptible state. Just in case any of you are wondering if you can receive a shot for something and then have to get another shot for it later, or even a booster. And yes, I did this right at the start of COVID because there I was locked in my apartment. I couldn't go anywhere. So what the hell I might as well do is sit here and play with these. And this one, people mentioned Shiny in art, which allows you to have widgets that control values. I just wanted to let you know that Python has these too. And by fiddling these values, you can change the parameters of your epidemic. And when you change the parameters of your epidemic, the main takeaway I got from this, I was trying to see if without even looking at the math, could I ever get cyclic behavior? Briefly, the answer seems to be no. Once you have the parameters set for your epidemic, it's going to reach an equilibrium. And if it is possible for recovered people to become susceptible again, your equilibrium may end up looking something like this. You are always going to have infected people. You are always going to have people who are recovered, but you will always have people in all the other stages as well. And it seems to be a stable equilibrium. From wherever you start, it will settle down to these values. So watch your newspaper, watch the COVID data, and someday, perhaps next summit, I can show, if you download those notebooks, it includes one which downloads COVID data, live COVID data each day, updated by Johns Hopkins University for the US and globally. And the US, it's broken out by state. Globally, it breaks it out by country. And you can draw your own graphs and satisfy yourself whether we're coming to an equilibrium here. Any questions in the last 14 seconds or whatever we have?
Well, if nobody has any questions, then thanks, Andy, for sharing with us today this data analysis. Definitely people in chat said it was very useful, so that's good.
This is just, a lot of times you're given data and you don't know what it is.
Mm-hmm.
And you don't know how good it is, and you don't know what quality it is. And these, it's not just for messing with data, it's beautiful tools for determining what your data is and whether it's worthwhile, and then messing with it and doing the graphs and charts and statistics.
I believe Prime of Canada said it would be a good Twitch channel.
Anyway, I thank you all very much for attending, and I now pass you back to our good hosts.
So, hello everyone, I am Iqra Ahsan and I'm currently doing Bachelor's in Applied Biosciences. I am from Islamabad, Pakistan, and I welcome you all to my presentation and I hope you guys are doing good. I will begin my presentation by this quote by Richard Feynman, which says, "There is a plenty of room at the bottom." Now here is, next slide. Here's a poster for my presentation, Miss Sandy, a biomimicking robot, a guide to making a nano robot. There's a fun and interesting story behind this. So growing up, I love watching SpongeBob SquarePants, and they used to be one of my favorite cartoons. So inspiration behind this is that. And the cartoon character here you can see in the corner is named Sandy. And a fun fact about Sandy is that she's a scientist and innovator working in the bikini bottoms in SpongeBob. I will explain why I choose her later in my presentation, but for now, let's just remember her name, Sandy. Next slide. Now you guys must be wondering, what are these nano robots that I'm talking about? In a very easy term, nano robots are made up of very small particles that are 10⁻⁹ of a meter. And the particles are known as nanoparticles. Yeah. And nowadays we use oral medicine, injections, etc. to cure diseases. And in future, medical nanotechnology is expected to employ these nanorobots that are injected into the patient's body to work at a very small cellular level. Next slide. I will explain briefly some of the applications of these nanoparticles. In medicine, they are used as nanorobots in nanosurgeries, in therapeutics for various drug delivery processes, and in diseases diagnostic and detection, including molecular imaging, and in nano implants for bone tissue engineering and of course, in cancer for targeted therapy and gene therapy. Next slide. Okay, so there are various kind of nanoparticles that are made of metal ions, organic, or liposome nanoparticles. And usually in case of cancer, chemotherapy is used to treat cancer. And basically what happened in chemotherapy is that both healthy and cancer cells are destroyed. And you could see very evident side effects like hair loss. So we can solve this problem by using nanoparticles, which will act as a nanorobot and will deliver drug to cancer cells and can destroy them. So I will explain with the help of a diagram here how nanoparticles like liposomes are used as drug delivery vehicles for targeted cancer therapy. So basically what we do here is we first made a liposome nanoparticle, then we make it functionalize liposome by attaching specific biomarkers that are also present that sense the cancer cell. Then we load our anti-cancer drug into these liposome, and we can enhance their permeability and retention effect with the help of magnets or sometimes the help of ultrasound stimulation. And as a result, these drug-loaded liposome enters the cancer cells, and here they disintegrate, and the anti-cancer drug or whatever that we have put into it destroy the cancer cells. So in this way, we are only targeting the cells that are producing cancers in the body. Next slide. And the reason I used Sandy in my poster was because of mesopore silica nanoparticles. These silica nanoparticles have very interesting properties because they have very ordered porous structures, and they have huge surface area, and their size particles can be tunable. And they are very good biocompatible. They have very good biocompatibility. So they're used to increase the bioavailability for poorly soluble drugs, and they are also used in cancer therapy and gene therapy as well. Now I have tried to explain the science behind these magical nanoparticles, and you guys must be wondering, what is the easiest way to make a nanorobot? Next slide. So how to make a nanorobot? Next slide. I will give an example of cancer-killing nanorobots. Next slide. So here is a diagram. Don't be scared. I will just break it down into very simple, tiny information. So first, what we do is we take rectangular DNA sheets or origami DNA sheets, and then we attach these green particles. As you can see on the diagram, these nanorobots include a special molecule, a DNA aptamer, that targets a protein found in high amounts only on the surface of tumor cells. And we also attach a thrombin molecule to the DNA. And these thrombin molecules, I am pretty sure you guys have heard about it. It's a blood clotting enzymes that is naturally present in our blood as well, that is used in healing of wounds and etc. Okay, after that, we fold this DNA sheet into a hollow cylindrical shape. And then this hollow cylindrical shape have these special green DNA aptamers that can sense the tumor cells. So when they enter the tumor cells, they disintegrate or unfold itself, and thrombin gets activated and start the whole process of blood clotting. So as a result, it restricts the blood flow to the tumor, and the tumor cells get destroyed. So this is the whole way we can design a nanorobot, and it's specifically cancer-killing nanorobots. Next slide. So I have a little activity for you guys. I want you to think about any crazy nanorobot idea. You can unmute yourself and share your idea, or you can send in the chat box. I have 3 or 4 minutes for you guys. Come on, it can be anything. I think someone messaged in the chat, cultivating specific microbiome members. Okay, cool. Yeah, this is a very cool idea, photosynthesis nanobots. I like that. Okay, so you guys have shared your idea, so I will share my idea. Next slide. Same, I would love to have a nano robot that can give me, good hair and shiny skin. I would love to have a nano robot that can, make me smart or make me emotionally intelligent. Yeah. Yes, actually, research is being done on this, delivering drugs to Parkinson's disease patients. Yeah. Okay, I love this idea of nanobots to have a Spider-Man suit. Okay, next slide. Next slide. So this is it. Thank you everyone for listening.
Thank you so much, Iqra. Do anyone has any questions? Anyone has any questions? You can raise your hand, or you can just ask. You can also use the chat section. I am with Eric on having some microbes that can have our hairs back, and yeah.
Bring back hair as some sort of stem cell function, right?
Yeah, that is a cool idea.
Zoe has a question in the chat.
Oh yes. So you asked, which are the interesting labs that are studying nanobots for cancer now? I think there are some labs at Germany and in US that are working on these nanobots.
What cancers are being targeted first? Kinds of cancers.
There's a lot of work being done on cervical cancer and breast cancer as well. But the most I have read about is cervical cancer and Parkinson's disease as well. Because nanoparticles have this, because they are very small in size, so they can cross the blood-brain barrier. And usually in medicines, it's really difficult to cross the barrier and enters into the brain. So a lot of work is being done on Parkinson's disease as well.
Have they been having good results with Parkinson's?
They haven't done any clinical trials yet. The experiments are being only done in vitro, and yeah.
So any treatments that would result are quite far down the line in time?
Yes, yes. because they do have sometimes certain drawbacks, since again, they are very small in size, so you don't know the how the drawbacks that can occur, because they can cross blood-brain barrier and they can seep into your blood vessels and all that. But there has been some promising results because of the targeted therapies been given by nanoparticles.
We have another question from Seren. Are the labs and animal-based experiment for Parkinson's looking promising?
Yes, they are looking promising, but they haven't been approved by FDA for clinical trials.
You mentioned some potential drawbacks of having the nanobots in the, in the system. Is there any way to like turn them off after they've done their job or anything like that?
Yes, some nanoparticles are biodegradable, like liposomes, etc. But if we're using metal nanoparticles for drug delivery, so they last very long, but these are sometimes get removed from the body, like usually the mechanism happening in the body, for example, in kidney and urine formation. But metal nanoparticles have a range that you can administer. Because if you administer more than the range, it becomes toxic for the body.
I'm curious, what metals are used and in what applications would you use metal versus like liposome?
Recently, I've also made nickel oxide nanoparticles. So nickel oxide nanoparticles has been used as an anti-cancer and an antimicrobial agent for cervical cancer cell lines. So all these experiments are being done on the cell lines. It also depends on the disease you are targeting.
All right, everybody. Thank you so much, Iqra, for that amazing workshop. We will be having a 15 minutes break, and then we have another presentation. So stay tuned, and yeah, see you in 15 minutes, guys.
Great. Well, welcome everyone. Glad to see so many of you here. So my name is Jenny Molloy. I am a researcher at the University of Cambridge, and my group is the Open Bioeconomy Lab. So we build open source toolkits for biology, mostly working with collaborators and colleagues in lower resource labs in Africa and Latin America primarily, but we're interested effectively in seeing how the distribution of open source toolkits and protocols and associated kind of support and learning materials could help places where the bioeconomy has not fully developed to kind of build up their capabilities and resilience to actually develop their own enzyme, protein, recombinant expression systems. So we are going to present today, well, I'm going to present today. This is the work of many collaborators, so I just want to thank them. But I'm going to present today our open enzyme toolkit. The idea is that we have a select set of enzymes that we've produced. They're mostly enzymes that are really useful for molecular biology. But the idea of the toolkit is that people can add to that. So I mean, ideally, what we'd really want to see in a few years down the line is that people have taken the toolkit and added enzymes that they've found in their own environment to produce really interesting applications that we didn't even think of to begin with. But we thought the place to start was molecular biology reagents, because they are the tools that fuel that downstream work that could have some real world impact. Another interesting thing to note is that a lot of the enzymes that we produce for work in the biology lab also have application in diagnostics. So this has become quite a hot topic in the last 18 months as COVID-19 has caused a lot of supply chain issues. And so some of our work in the lab has shifted towards diagnostics, but the path from having an enzyme that is suitable for research use to having an enzyme that is suitable for diagnostics use is a long and complicated and expensive and difficult one. So today I'm going to be presenting basically really like education and research grade enzymes, how to produce them at relatively low cost in a standard molecular biology lab, so no fancy equipment required. And then we'll also have the opportunity to do a little workshop demo on Benchling. If you do not have a Benchling account, you can view the sequence files, but you won't be able to copy them into your area and kind of do the exercise. If you do have a Benchling account and you would like to do the exercise, we'll see how timing is going. So if you have the luxury of a screen that's big enough to put me in one corner and look at your Benchling at the same time, it will be possible to follow along. If you don't have that luxury, then you can feel free to just watch the walkthrough, and the sequences are available for you to go back and do that at any point. But if you don't have a Benchling account, you feel like you might like to follow along, it will be a good idea during this first part of the presentation to sign yourself up on Benchling. I don't think it takes very long. It's quite simple. I did it earlier today to double check. So you just provide your email address, they'll send you a link to click, and then you're in. So I recommend that if you do want to go along. But yes, as Tim's I think mentioning in the chat, if you have the super luxury of a dual monitor, then you'll be really rocking during this particular workshop. I am fortunate to have that, but I'm actually on my laptop today, so unfortunately I don't have it for the demo, which is quite frustrating. So I'm going to start my presentation now and talk you through a little bit about how to use the open enzyme collection. It's actually going to start on Benchling, I've just realized. Oh, there we go. Okie dokie. Perfect. Okay, so as I just mentioned, this is a presentation working with the open enzyme collection for frugal biomanufacturing. I've already said my name. This is my contact information, so feel free to get in touch if anything during the presentation piques your interest. If you'd like a collaboration, you'd like to put in touch with people, more information, do reach out. That's also my Twitter handle there as well. So I already mentioned I'm based at the University of Cambridge, but I also work with some amazing communities around the globe, some of which I'll mention later, but some of which are listed there. So Open DNA Toolkits. What is the Open Enzyme Collection? So this is basically a selection of different blocks of DNA that you might need, particularly to express proteins, and particularly to express proteins that are enzymes, and therefore you might need to do some processing with them downstream. So this is a project of my lab, but many collaborators, too many to name here, but they are listed on our website. It's all been synthesized by Free Genes, which is a project at Stanford University supported by the BioBricks Foundation. And I mention that partly because, as I'll come back to later, you can actually get all of this DNA for free from Free Genes. But one of the main characteristics of a Free Genes collection is that it's distributed under the Open Material Transfer Agreement. And for those of you who are based at academic institutions and are just going to do research with these proteins, that's maybe not so big a deal, but it has two distinct advantages from the normal way that you get DNA from, say, for example, AdGene, although I'll come back to AdGene shortly. It's that you can redistribute it, so you are completely within your rights to pass it on to whomever you like from your local community labs, local institutions. And the second thing is that you can use it for commercial use. And so what we're really hoping to see is that this can form a resource for small biotech companies that need to express enzymes either for their own R&D or to supply in their local regions. So it's fully available for commercial use. And as I mentioned, AdGene is another place that you can also get the Open Enzyme Collection, and under OpenMTA, because AdGene have now added the OpenMTA to their list. So that's really great. We have a selection of different, well, enzymes for starters. So the actual coding sequences for the enzymes. As I mentioned, they're primarily at the moment useful research enzymes. So we've got quite a few DNA polymerases in there for different purposes. We've got ligases, reverse transcriptases. There's a whole collection. I can show you more on the website to show you how to navigate the lists. We also have a whole collection of reporters, so fluorescent proteins, chromoproteins, enzymatic reporters, and then basically parts that are useful for expressing and using the collection. So we've got tags to bind to different substrates for purification. The classic is a his tag. Any of you who have done protein purification before have probably come across that one. But there's also some interesting ones that mean you could bind your protein to cheaper materials. So there's silica binding in there. Silica is very readily available. You can even purify it from sand if you happen to have sand nearby. It binds to cellulose, so basically filter paper or other forms of cellulose. We have a number of these options if you want to try out a lower cost purification route. And then there's also just handy little things, pieces you can snip your enzyme off of the immobilization tag. So we have inteins and TEB protease sequences. I won't go into too much detail because I don't know how the background of everyone in the workshop, but if you have specific questions about what these parts do, we can dig into that a little bit later on. So that's the basic collection. And the idea of this is that, you know, we provide the parts, but it's your choice how you put them together. So you've got nearly 200 interchangeable elements across the whole series of collections that you can combine in any way that you would like. And I just wanted to point out that one specific kind of special collection that we made is the research and diagnostics collection. And so this is a collection that's specifically designed for those who are researching diagnostic assays. And it's effectively a subset of the open enzyme collection with some extra bits added in. And so you can see here, for example, there's a number of coding sequences for sort of enzymes that are useful for PCR, like OpenVent, which we'll come back to a lot later on, BSTLF, which is a LAMP, isothermal amplification, useful enzyme, a couple of reverse transcriptases, which are used for most RNA-based tests, for example, COVID tests, and then a number of others that are used in perhaps slightly more obscure amplification methods like RPA. But this is a kind of fully formed collection in the sense that we actually put all of the correct bits of DNA flanking these parts so that you can easily assemble them. And so we made this syntax, which is kind of copied at the bottom here. So basically, this represents, we've thought in advance about the order that you might want to put the parts, and we've designed overlaps within the sequences such that when you cut them with BSA1, which is a restriction enzyme, they'll actually fit together in the order that you expect. And I'll come back later to, if that means nothing to you, don't worry, because we're going to talk about DNA assembly again in a second. But I just wanted to point out that that's a really kind of nice sub collection that you might want to use at a certain point. So where to get the DNA, I'm going to show you where to get it, and then we'll just go and look in the browser at how to find the sequences as well, because you can also resynthesize it if you need to. So all of our enzymes are designed to be expressed, and all of the parts are designed for E. coli. And there are other projects looking at yeast. So Scott Pownall has a talk during this session, unfortunately, but also I believe a workshop tomorrow about the Open Yeast Toolkit, which is a very similar concept, but all about yeast. So do head on over to his workshop tomorrow if you want to find out about these sorts of collections for yeast. His collection focuses a little bit more on metabolic engineering rather than sort of enzyme expression, but there's also a lot of effort gone into having parts for Bacillus as well. Bacillus subtilis is quite a nice enzyme expression organism as well, because it's quite good for pumping the enzyme out of the cell, extracellular expression, very extracellular transport, and so you can collect it from the media rather than having to lyse the cells, which is very nice. For us, we stuck with E. coli because it's a really well recognized molecular biology workhorse. Almost anybody who is doing molecular biology will have some E. coli in their lab. And so that was why we stuck with that. But we do recognize that there are other organisms which might be useful. So if you want to get the DNA, you can order it from FreeGenes. So just go along to stanford.freegenes.org, and literally for free, you can add it to your basket and have it shipped to you for free. So there's no shipping costs, there's no cost for collections. It will just arrive with you an amount of time after you order it. You can see here that the collections are actually broken up, so do have a check within each one if it contains what you want. We have 2 open enzyme collections, 1 collection of open reporters, and then, as I mentioned before, the research and diagnostics collection is a separate collection, but you can find them all on the website and just go in and find what you need. Very, very recently, as of I think about 10 days ago, you can now also get the collection from Adgene. So you can head on there. Adgene do charge for the collection, but they're also going to be around for longer than the Free Genes project, which is a project. So it's a at the moment a time limited initiative. So Adgene will keep these things rolling. You can also on Adgene get only the bits that you need, so you don't have to order the whole collection at once. If you order it from Free Genes, you can't pick and choose. They will send you the whole thing. So just be aware that there are different routes of the ordering. And now, before I carry on with the whole presentation, I'm just going to escape from here. Move the annoying Zoom controller, which is always exactly where you want to click on the screen, I find, and just show you how to find the parts that you might want. So my lab's website is openbioeconomy.org, and you can head on there. Again, see, it's just if I've moved it to exactly the point that I need to press again. Right, let's go here. And in research, you'll be able to find several references to the open enzyme collection. I'll just use this link here, featured project open enzyme collection. And if you head in here, you'll find some information about what's in each of the collections. And then down here, you can actually click into each of the Google Docs that we have. We are looking at having a somewhat more sophisticated database. So if anyone's interested in that, get in touch. But for the time being, they are in Google Docs, which explains kind of what the column headings mean. But then if you go into the DNA polymerase is the sheet, don't know why there's extra sheets in here, then you can find all of the enzymes that are here. You can also find out the original patent. So all of these, the patent is expired. That's why we can make them fully available under the Open MTA. And you can have a look at what they're used for. There's also links to the original paper that describe the patent, that describe the enzyme, more information about the patent. And if you go along, you'll find the link to the sequence here on Benchling, and where applicable, a UniProt ID as well, if you want to investigate the protein itself. So that should be useful information. So if you do want the sequence in order to check anything or to change some bits and pieces and resynthesize it, you can find it from here. I'll just stop sharing now. And then the Open Research Collection actually has a quite handy schema, which is linked to the Free Genes. I'm just going to bring it up now. But that actually has a nice clickable interface so that you can find what you want and click through to find the sequence directly from there. So let me just show you that as well. Here we go. Yeah. So again, this is all on a Google Doc. We are planning to make it more web friendly, but at the moment, this is the Research and Diagnostics Collection. You can find the parts list here, which, sorry, my computer is being slow, which explains what all the parts are, what they do, any notes or useful information, what kind of protocols they're useful for, and links to the Benchling files are here as well. And then the very useful thing is the DNA modules scheme. So as I mentioned before, this is designed such that you can fit things together in the order that you want them. And so in here, you can actually find out what fits in each of the gaps. So you can go along and say, okay, well, here are all of the coding sequences. They go between points C and D, and you can scroll down and click through, and you'll find yourself on the Benchling file for those as well. And if you scroll down here, so sometimes, for example, when we put this together, some enzymes need particular parts like a purification tag on the N terminus and some need it on the C terminus. So we have to be a bit flexible. So that means that you might have nothing, for example, between D and E or D and F, because those are the bits where you put a tag if it was needed there, but you might put it at the other end. So if you scroll down here, you'll see that we've also got linker sequences that basically it's just like a dummy bit of DNA that you can stick in. Some of them do have functions, so they basically have one thing, but they span like 3 slots, if you like. But basically, when you assemble something, you need to get between F and A, or A and F. And so whatever you string together, it's got to have an A at one end and an F at the other, and all link up in the middle. So this structure on the spreadsheet hopefully shows you kind of what options you've got basically in assembling all these pieces together. The other thing to note is that of the original Open Enzyme collection, not all of them were built with this syntax in mind, because we only put it together last year when we did the research and diagnostics collection. So it doesn't mean they're incompatible. It just means that if you order our other collections, the earlier ones, you can still use this, but you'll have to design some primers that basically add these sites onto the piece of DNA and put in a BSA1 restriction site and PCR it just to add those on either side, and then you can use them exactly as anything else. And so it's quite functional in that way. So I might pause there for a second just to see if anyone has got any questions. If it's questions about DNA assembly, hold your horses, because we're literally about to go to that on the presentation. But is there anybody who's got any questions basically about what's in the collection or where to get it? Feel free to raise your hand or pop something in the chat. I'm afraid I have not been monitoring the chat while I've been speaking. So please make some indication. Danny, has there been anything in the chat that you've seen, or other organisers that I've missed?
No, I think you're good in terms of questions.
Okay, great. Oh, I think I see one raised hand.
Yes, I have a question. I'm from Serbia. It is outside of EU, and it's so really big mess if you want to import anything to Serbia. So my question is, can we make a collaboration? Or how to deal with those stuff? Or
very good question. Yeah, so if you want the collection delivered to Serbia, I mean, Free Genes, to be honest, have done a very good job at getting this stuff all around the world. I know that it's been sent to at least 40, probably now more closer to 50 countries, including a number of African countries that also tend to have quite strict regulations. So Free Genes are good. If you want to guarantee it getting in, Adgene are extremely experienced with shipping stuff to all corners of the world. So they have a whole team of people that know how to do that. So I would recommend trying from Free Genes first, because they will do their darndest best. But my assumption is, if it's going to go wrong, it's going to get stuck kind of once they've shipped it and when it reaches Serbia. If that doesn't work, then I would try Adgene, because they really are experts at it. And you can always if the cost of the collection from Adgene is a challenge, you can always contact Adgene. They do have various schemes and kind of options for those who can't afford their services. So it's worth a chat with them. They're obviously not free, is the point, but they're actually very reasonably priced. I mean, they are a non-profit, so they don't have astronomical prices like a commercial supplier might. I hope that helps. In principle, if anyone kind of that is in a country and you're likely to visit it, you could also try and figure out some kind of sneaker net way of distributing via collaborators as well. I think two more participants, Adrian and Eric. Yeah, so Adrian, go first, then Eric, and then we'll continue with the presentation, if that's okay.
So I looked at the documentation, and there seems to be several, like 4 or 5 documents for each of the genes there, and sometimes they don't match. Is there any way to know which one is the primary source of information? And this is true especially for earlier collections. I think the diagnostics ones is probably the best documented at this point.
Yeah, absolutely. The primary source of information is those Google Docs that are linked on the website. So if anything in there does not match with your knowledge of what you've received, then let me know and we can fix that. But that should be the canonical source of the sequence information. As I say, we're working on getting it not in Google Docs, but in more of a searchable database, which should make it a lot easier. But, you know, as ever, people and funding are the main restrictions on being able to do a better job on that. We are working on it. It's very high up my guilt index at the moment, so I'm trying my best. I'm hoping come January that we'll have somebody here in Cambridge who'll pretty much be full-time just maintaining and helping with the collections. And if that grant also comes off, then we'll have some funding to build out some better web infrastructure as well. So I hear you, but yeah, we also rely a little bit on users to kind of feedback to us. I have a very small team, so if you see anything, flag it. And we've had some amazing people that have got back to us. I mean, you know, when you do something like this with like 60 odd enzymes, something's bound to go wrong. And for example, one of the enzymes had one amino acid residue that had been missed when we truncated it from another sequence, and unfortunately for almost anywhere else in the protein it would not have mattered. It just happened to be like this one piece of protein that really did matter. So what we've done, we've resynthesized the correct one, and we've changed and kind of let well, people who already have the collection, we asked Free Genes if it's possible to email them. I think at the moment it's not fully in stock, so I'm not sure that they have done that yet. But at some point, if you've already got a collection, you should have a message saying, hey, if you want to use this, you'll need the new version, so let us know. We're obviously not resending it to everybody because people may not actually want that protein. But yeah, we do rely on feedback. So, and we take it well. We'll hold our hands up and say, yeah, we got it wrong, we'll fix it. So do let us know.
Thank you, Jim.
Thanks for your question, Adrian. Really helpful. Eric, you had your hand up. Oh, you are not audible.
Do you hear me now? Okay.
Yes, now we hear you. Yeah.
So a quick question. You are a little bit more interested in the CDS and the enzymes, but I want to ask you if the reporter proteins and the rest parts, the promoters and the terminators, also lack any PI restriction, IP restriction?
Yeah, the entire collection we have screened for any patent that existed has expired. Yeah, in some cases they were deliberately without a patent. In some cases they're so old, like patenting wasn't even a thing. But yeah, no, all of the collections are free of any intellectual property that we are aware of. If you do plan to kind of pop it in some kind of product that you then want to use commercially, we are not lawyers. We have done our due diligence as far as we can, and we've provided the links to all the patents that we believe covered it and are now expired. But yeah, always helpful to have a lawyer check it over. But as far as we're aware, everything in the collections is not covered by patent-based IP, and also because you receive the collections under the open material transfer agreement, there's no kind of material transfer restrictions either.
Okay, thank you.
No worries. Okay, so we're going to move on to DNA assembly. So I am not sure how many people have experience with DNA assembly. So what I'm going to do is just going to see how many people I can fit on one screen on my grid, and just ask that if you would describe yourself as reasonably fluent in assembling DNA, and I'll tell you we're going to talk about type 2S assembly methods and Gibson assembly methods. If you'd say that language that you understand, could you use the raise hand function or some kind of emoji based communication method, and just let me know that you are happy with all of that, just so I get a sense of who in the room is confident in DNA assembly. So go. All right, I'm seeing a few. Oh, that's handy. Zoom puts you all up on one row. Okay, so I'm just going to scroll and check. I'm seeing about 5 hands that are confident in that. Okay, good to know. Great, thank you very much. So we'll go through this in a reasonable amount of detail and also talk about the benchling practical exercises. So the first way that you can assemble stuff that you get in the collection is commonly called Golden Gate or Mowoh assembly, but it's basically using a restriction enzyme. I'm going to show you a diagram-based explanation, and then we're going to watch a video. So depending on what your learning style and kind of how you like to visualize these things, hopefully one of these will tick your boxes, but if not, we'll do another question session at the end. So there's two ways you can do it. The research and diagnostics collection that I just showed you and demonstrated, you know, all those A, B, C, D, E, F kind of chunks basically along that. That's all because we have a system that allows you to do this type 2S assembly. And type 2S is basically a type of restriction enzyme. So restriction enzymes are just enzymes that cut DNA. They identify a particular site within the DNA and they cut it. Sometimes they cut it straight across, sometimes they leave an overhang. The interesting thing about type 2S enzymes is normally restriction enzymes cut within the site that they recognize. So if they recognize CATG, something like that, they might cut between the A and the T, but it's within the site they recognize. So if another restriction enzyme comes along, for example, and it's already been cut, then it's not going to bind because it's kind of destroyed its own cut site. The type 2S cut sites, the type 2S enzymes are a little bit different. So they actually cut the DNA outside of where the enzyme binds. So if you look here, this is the type 2S recognition site where the enzyme will clamp on, but it doesn't cut within that, it cuts outside of it. And it doesn't actually care what nucleotides are outside of the site because it's not part of its recognition sequence. So all of these N's here just mean that they can be A, T, C, or G. The restriction enzyme literally couldn't care less. So that's very handy for us because it means that we can put nucleotides in there that will then base pair with another sequence because they overlap. And so what you've effectively got if you get plasmids from the research and diagnostics collection is a backbone, plasmid backbone. And then you've got your piece of interest, maybe your enzyme that's here in the middle. You've got your recognition sites, and then what we've done is we've actually calculated, we've added these 4 base pairs such that they pair together. So when you see the letter A on that schematic, what it means is that there's the A set of the A set of 4 bases will match with the other A set of 4 bases. So that's your kind of A junction. And so if you put A and A together, they'll actually stick when you put them in the one pot, and they'll overlap because the base pairing will work. And the A set of 4 nucleotides is completely different to the B set of 4 nucleotides. So you'll end up with a part that has the A and the B set on one end, and it will match with the A, and in our case F side, and it will match with the B and the C part. So they sort of stick together. We'll come back to this on the video, it'll be easier at that point. But you can see here, so you've got your N's that could be anything. They're actually, when you go back to look at the structure that I showed you earlier on that spreadsheet, you'll see the different four pieces that we told. When I say they could be anything, they actually couldn't be anything because not all 4 base pair overlaps have equal efficiency. so there are preferable ones to use, and NEB did an amazing paper where they basically looked at many of the 4 base pair options, combinations, and kind of picked the best ones that will give you the most reliable sticking together, and those are the ones that we've used in our syntax, so hopefully it's quite efficient. But when you cut, so remember your enzyme is going to bind to this brown site, and it's going to cut the recognition site, sorry, bind to the brown recognition site, and then its cut site will give this overhang. And so you can see here, so green is one set of 4 nucleotides, doesn't matter which, but blue is a different set of 4 nucleotides. And so you'll end up with the part cut away from the destination vector. And then basically what you do is just repeat that with all of your parts. And so you'll end up with a vector, one piece that basically acts as the backbone, which in our syntax is A to F. So this is the green one is basically A, and the blue one is F. And then over here, you've got a part from another piece of DNA that you've done exactly the same thing to, you've digested. But in this part, you've got A here and a completely different one here. And then basically you just keep sticking them together until at the end, you have to have the blue part, you have to have F. And so you end up that because the 4 base pairs overlap, you end up with them in this order. And they can't go in any other order, because if this one here, this red part, tried to join here, it can't, because they don't overlap. So that's how you basically make sure that everything's in the right order, and that your parts are assembled correctly. So I'm just going to show you without sound this video, which is, NEB have great videos, by the way. If you want to know about DNA assembly, they're really well illustrated. I'm not going to put the sound on, I'm going to talk. So let me just check that the sound is not going to, I'm assuming this, you can't hear anything. Correct? Okay, perfect. So this is what we've just talked about. It's basically the same thing as I've just discussed, but it's video format. So here we go. That's the type 2 nuclease. It's attached to that recognition site, and it's cut these N fragments there. Destination vector, again, they've chosen 2 insert fragments, but it doesn't have to be 2. You can have any number in the middle. And we're going to use BSA1. So you can see here that it binds these sites and cuts that sequence there. And now it's going to do the same thing for the insert fragments themselves. This is just explaining that if you don't have, as I mentioned before, the restriction site and the overlap piece, you can add them by primers. Just make primers that have those on the end, do a PCR, and then you've got the right DNA. So here we go. Magic. So now we've got PCR amplified fragments that have the right pieces on them. All of this can go into a single tube, because remember, it can't pair incorrectly is the idea. So you can just do it all in one go. It gets chewed up by the BSA, and now you can see again, we've got the overlaps, they all stick together, and they give you the assembled DNA product. And then NEB will go on to tell you that you can't get it wrong, and also that you should only have linear DNA assembling. Remember, because it cuts outside of its recognition site, you've actually removed the BSA1 sites from the pieces that you're putting in, so they're disappeared. That does mean that you can't then redigest it and reassemble it another way. For example, you'd have to go back to your original parts, or you'd have to PCR out of this final vector again to give you those sites once more. But you can see you need 2 different enzymes in the tube. So you need the BSA1, which then does its digestion. And then in order to assemble the product and knit that cut DNA back together again, you need a T4 DNA ligase. So hopefully that made sense to most of you, particularly those who haven't done so much on the assembly point before. So just to summarize, you need to isolate your plasmids from the collection, whichever ones you want. Very handy to use that schematic to pick which ones you need. You're going to use the BSA1 restriction enzyme to create the fragments with overhangs, and then T4 ligase to ligate the fragments together. And both of those enzymes are in the collection. So once you've done your first kind of set of expression, you'll actually have the tools that you need to carry on round. Caveat that BSA1 is a nightmare to express. Unfortunately, you might figure out why it cuts DNA, which is a bad thing if you're an organism that depends on DNA for survival. So BSA1 is, if you try to express BSA1 in a micro...
I'm really sorry to cut you off, Jenny. Yeah, your voice is very distant.
Oh, did it suddenly do that?
Yeah, it dropped at one point about 30 seconds ago.
Oh, sorry, Zoom.
Now it's good. Now it's good.
Okay. Yeah, for some reason Zoom changed microphone. Very strange. Apologies for that. Hopefully it's good again now. So yeah, if you try to express BSA1 in a microbe, you'll actually need another enzyme called a methyltransferase to protect the microbe's DNA from being chopped up by BSA1. But if you have a cell-free expression system, you can do without worrying about that. So there's a couple of options that you have there. Right, hopefully. Okay, there we go. It went too far. So how do you put it together? Well, here's a mix protocol. Not expecting you to remember this, but this is actually from a very nice guide that the iGEM Uppsala 2020 team did to Golden Gate Assembly, which I'd recommend reading. If you want to put more than one kind of transcriptional unit, so that what we designed in the research and diagnostics collection basically enables you to put all the bits together to express one protein or one enzyme. Sometimes you might want to have more than that. In that case, the thing to explore would be loop assembly, which can enable you to put more on. This is kind of more advanced DNA assembly, so I just leave it as a reference for those of you who are kind of interested in taking things further. The other option is Gibson Assembly, is what most of you will know it as, but I'm going to talk here about Klenau Assembly. But basically, it's a way of, instead of having the overlaps that are produced by a restriction enzyme, you add the overlaps on by primers. They have to be quite a bit longer, but you basically design a primer that has kind of, that it attaches to your DNA of interest and then has a tail on the end of it. And then that tail is complementary to the next piece of DNA that you're interested in stitching together. The downside of this is that you have to design a bunch of primers. So each time you want to do something, you've got to design more primers. The positive side is that you don't need necessarily, you've got a little bit more flexibility, basically. So for some things, particularly if you're only assembling a few bits together, this can be quite handy. I'll explain in a second. So Gibson Assembly and Klenau Assembly are effectively the same. They both involve these primer-based overlaps. But when you use Gibson, you actually have to put a number of enzymes in the tube. With Klenau, we use Klenau DNA polymerase, which actually has both an exonuclease and a DNA polymerase function. So in Gibson, you put an exonuclease and DNA polymerase in separately, along with a ligase. In this case, Klenau performs both of those roles. And the only thing it leaves then is a nick in the DNA because you haven't added any ligase in, but you actually just transform it then into E. coli and rely on the endogenous E. coli ligase to do the trick for you. So it's a cheap version basically for the undiscerning and lower resourced lab. Gibson is more efficient, but you know, Klenau does work. I mean, we use it routinely in my lab in Cambridge and it works pretty well for most things. And it saves us a lot of money on Gibson kits. So just a little tip. And again, both Klenau and the PCR DNA polymerases are in the collection as well. I put the link here at the bottom. I will share the link for this as soon as I finish the presentation. I'll stick the link in the chat. So again, it's only B because their videos are great. So just to illustrate how this works, again, this is talking about Gibson Assembly. Ours is exactly the same, just the enzymes are going to change. Here are your two fragments that you want to stick together. You can see they basically added complementary DNA on the ends there using PCR. So they have an overlap. They're going to stick it in the Gibson Assembly. You're going to incubate it 15 minutes to an hour at 50 degrees. And what's happening during that time is that there's actually an exonuclease that's going to start chewing back like that. So you actually get a single-stranded overlap now. So obviously you need that for base pairing. So those are your complementary regions that you added with your primers. They start sticking together just out of base pairing. And then your DNA polymerase comes in and off it goes and fills in the gap. But it does leave these little nicks, which are sealed by DNA ligase. And then you can kind of move on and do whatever you want with that. And obviously if one of those pieces is your backbone, then you're going to end up with a plasmid with a whole circular piece of DNA with just a couple of nicks in. Stick it in your E. coli. Bit of advertising for NEB there, but they do really good videos, so I think we'll allow it. And I think that ends there. Yeah. So then they just talk about how good Gibson is. So hopefully that made a bit of sense. I'm aware that we don't have a huge amount of time to go through. So what I was thinking was we could just do a little bit of a vote on whether we go through Klenau or we go through the type 2S on benchling. So maybe we'll have a show of hands or emojis for who wants to look at how to get your Klenau assembly designed on benchling. Hands up. We'll have to move quickly on this because we're going to jump ahead. So it's going to do, I know not everyone's going to vote, but we'll do it 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, we have 4 votes for Klenau. Okay. Now remove your hands if you just had them up. Hands up for doing the Golden Gate / type 2S. 1, 2, any more? I'll do 5 seconds. We've got a clap as well. That's 3. We're currently 4-3, 4-4. Oh, this is no help. Okay, who's going to make the deciding vote? Oh no, we've ended up in a draw. This is terrible. My plan has failed. All right, I think we might have got one more clap then. All right, so okay, I'm going to make a deciding vote as there's clearly not a huge amount in it, and I'm going to say we'll do Klenau because the reason being, because of the way we design the collection, in that a lot of the parts already have the BSA1 sites in them, we're not kind of using the full power of benchling for that. So I'll show you in a second, but let me just go to projects. So here is a tutorial which is linked on the slides. And so if anybody does want to access the DNA, I'll just paste this into the chat now for you. So you can have it if you want it. Yeah, someone mentioning in the chat, there's a ton of these. There's so many. I mean, it would have been like a 3-hour workshop just to go through all the DNA assembly techniques. I just pointed to the 2 main ones that we use, but check out others, absolutely. So if you go to that link, you'll find this, which should be open to everybody. You shouldn't even need a Benchling account to look at it. And if you want to try yourself, all you need to do is copy the sequences into your own folder. So here, you can go copy to, and you can put them.
Jenny, I think you did not drop it in the chat, the link.
Oh, did it not go?
Yeah.
Oh, sorry, I've sent it to someone as a direct message. Sorry.
Worse.
I must have double clicked. There we go. Yeah, there you are. Yeah, there you have it.
Thank you.
No worries. Apologies for that. So yeah, here you can copy it to somewhere else. But for now, we're just going to go back and have a look. So these are the parts, and what I'm aiming for is one I prepared earlier, which is here. So I'm trying to do a open vent, which is a DNA polymerase, with a T7 promoter at the start. So that's expressed by T7 RNA polymerase. I'll come back to you later why that's a good idea, but if you use an E. coli like BL21DE3, it basically already has a system in the E. coli that produces T7 RNA polymerase in response to induction by IPTD or lactose. This is quite a nice expression system because you can use the strain to do a bit of the heavy lifting. We're also going to try and add a cellulose binding tag as well. And in this case, because it's open vent, we actually have to put it at the end terminus. That is where open vent tolerates tags. So that's where it's going to go. And then at the end, we're also going to have to put in a ribosome binding site and some of the kind of pieces that you need to do protein translation, to do transcription translation. And then at the end, we've got a T7 terminator. So I won't go into all of these pieces because we don't have time, but effectively what I did earlier is I went to that spreadsheet that I showed you. Oh, not that one, this one. And I picked out ones that would stretch all the way from A to F. And then if you go to the CDS, you can pick whichever of these sequences you would like to add. At the moment in Benchling, we have open vent. Obviously, these could do Golden Gate assembly, but we've chosen to just have a look at Claire now. So I'm going to go first of all to the backbone. So this is our backbone sequence here. And what you want to do in Benchling is go to the assembly wizard and create new assembly. And so here you can do Golden Gates, but if you do Golden Gates, it's going to come up with its own 4 base pair overhangs. That's what this system does in Benchling. So really you would want to be giving it kind of raw fragments that don't already have the overhangs and the BSA1 sites. If you want to try testing out your assembly with pieces that already have the BSA1 sites, instead you want to do a digest and ligate, and then basically you work along, and for each piece you have to select between the BSA1 sites, and then you can just make sure they all add up in the right order. So in a sense it's a little bit less exciting for our purposes because you're not really designing anything, you're just checking that what you've got is the right stuff and that all of your A, B, C, D, E and F parts stick together. And so instead we could do Gibson assembly. So we start here and we basically want to give it a backbone, which is going to be this one. So I'm going to look at the sequence map and I'm going to effectively tell it that I want this. I actually want between the BSA1 sites because that's the way it's been designed. But so we go all the way along. Right, so when you set a fragment, it comes up here, and then we can move along and insert different ones. So in our case, the next one that we want is the AB part, which is PT7. And then again, you can basically select it between, in this case, again, the BSA1 site. So you can see here that the piece we actually want is further along. Helpfully, we've labeled this random DNA, so don't select the random DNA, but you can come along. The problem with Clenau, which we will come across in a second probably, is that it's not very good for very short sequences. So typically speaking, it can't deal with anything that's less than about 100 base pairs. So that makes it a bit challenging for some of these small parts, which I believe this one is. So what you want to be careful of doing is, yeah, here we go, BSA1 is here. So the part that you want is actually only really between these two pieces, from here to here. And that is pretty small for a Clenau assembly. So it probably won't throw up any problems on benchling, but you may have trouble with that. A way to get around this would be to assemble some subparts together using a different technique, for example. But if you're just wanting to, if you've already got all your other parts and you just want to switch around the enzymes, then that's great because the enzymes are really big pieces. And so if you've already got an expression vector with all your little bits and bobs and you just want to take one enzyme out and put one in, then Clenau can be quite nice for that. You can always also use a restriction enzyme as well. And basically we just go through and we add each fragment. So you just go and select it. I've actually realized that given time, going through all of these is going to take a while. So, but what will happen when you've actually got one? What we'll do is we'll say that we've only, we'll say that we've actually, we'll say that we're not going to do all of these. let's say that. So if we remove that insert, okay, let's assume that we're just going to stick one piece in the backbone, but you can basically carry on and do anything that you like. So we'll say this is the test, we'll assemble it, and then it'll tell you, ask you where you want your primers. And so in this folder, I've already put an assembly primers folder. I say create, and ta-da, it's put your primers in there. So you can just go along and order those. And then do your assembly reaction. And so obviously if we'd carried on and put all the pieces in, you'd have one primer for the end of each piece. So as you can see, we've put 2 parts together, which is 4 primers. If we're putting 7 parts together, that's 14 primers. So it can get a little bit pricey, depending on how much it costs you to order primers. But you can go along and try this in your own time. What I wanted to do quickly is go through, because I realized we've only got 10 minutes of the session left, is say
you might be able to flex like 5 or 10 minutes into the
5
break.
minutes. Oh wow, okay. Well, I know people will have, I mean, I'm missing several sessions I wanted to attend, so, so I'm sure people will be having other plans. But anyway, we're going to go through, this really won't take that long. I'll kind of run through it and we can, you'll get all the slides and be able to ask me questions later. So I just wanted to explain how easy it can be to express, for example, OpenVent, which is our go-to DNA polymerase for like standard PCR. Many of you are probably more familiar with TAC DNA polymerase. TAC is kind of the original, but definitely not the best. So if you want a more robust enzyme that is 5 times higher fidelity, recommend OpenVent for your routine PCRs. The other great thing about making your own enzymes is it kind of doesn't matter if you make the really good ones and just use those all the time. So I would get quite annoyed at my lab if they started using Fusion or Q5 for every single PCR. But if you've just made enough, for like, it costs no more to make OpenVent than it does to make, for example, so Q5 is still very much on patent. Unfortunately, we do not have Q5 in the Open Enzyme Collection. What we do have is PFU SS07D, which is the non-trademarked Fusion, PHUSION, for those of you who are familiar. And the reason that's important is because for all of these things I just mentioned, you can add overhangs with PCR, you can add restriction sites with PCR. If you're doing PCR, for that purpose, you need it to be really high fidelity because you don't want to mess up your DNA sequence in doing that. And unfortunately, TAC DNA polymerase is pretty rubbish at making the right piece, the right sequence. So it's fantastic if you want to see if you've got something in or not, is the DNA present or not? go for TAC every time. If you want to use it downstream, it's not the best. So OpenVent is basically a TAC replacement. It's better than TAC. It's not very high fidelity. It's 5 times more higher fidelity than TAC. So I wouldn't use OpenVent for doing your if you're doing your sequence, if you're doing your PCR for cloning. That's probably not good enough for that, but it's good for just your basics. So and we're going to talk about doing it as a no purification cellular reagent. So in order to do this, you can get your assembled vector, which we just did in the benchling exercise, that has your OpenVent in it. As I mentioned, we did a T7 promoter. So the great thing about that is if you put it in BL21DE3 cells and induce those cells with either IPTT or lactose, they'll produce the T7 for you and start the expression. So you can do this in a number of ways. Typically speaking, you would grow up your cells in liquid on a shaking incubator, and after a certain number of hours at 37 degrees, you would add IPTG. We're lazy, so and we also want to bring down the cost of this stuff. So I'm going to show you a technique now that we've been trying for a while, which is basically using plates instead of liquid culture and using auto-induction media. So what we do here is instead of adding IPTG after a certain number of hours, at the very start, we put in lactose. And at first, the bacteria uses glucose as its energy source, but eventually it runs out of glucose. Then it starts using the lactose, and it's the byproduct of the lactose metabolism that actually induces the expression. So you typically get expression usually about 8 to 10 hours after putting on a culture. It's going to vary. You can use this technique in liquid, but you can also use it on an agar plate. And that makes life a lot easier for a number of reasons. So here's a little video. This is BL21DE3 on auto-induction media a night after it was basically been growing overnight. You can see it's really nice and confluent on the plate. This is on LB, doesn't grow so well on LB, so you want a nice rich auto-induction media. This is Chiara like not being very health and safety conscious and using a razor blade to scrape it off. You can use a glass slide or basically anything that's kind of, you know, has a sort of sharp edge, but it doesn't need to be as sharp as a razor blade. Other stuff does work as well and is less dangerous. So you scrape it off like this. That's all the cells coming off very nicely. As you can see, they just come off beautifully. It's actually quite difficult to break them, and then you can put it, in this case she's using a 50 ml tube. You can also stick it straight into a 1.5 ml. It depends how much you're going to scrape off in one go. And so this is what we're using, and basically you just put the plates at 37 degrees overnight, come back the next morning, and then you've got your cells there having expressed the protein. We've also found, so lactose works. I'm going to stop. Oh, sorry, I actually meant to stop the video, not stop sharing. Lactose works, but we've also tried fresh milk, dried milk. So any form of lactose containing good will typically work with this technique. And our colleagues in Cameroon are using dried milk, which is really available. It's room temperature stable. It's really easy to get hold of. So let me just, I always have trouble stopping videos on Google Slides. I don't know why. Let's see, just thinking about it. Okay, so you have done that and you scraped off your cells. What happened next? I will reshare my screen and show you what happened next. There we go. Right. So we use a technique often for standard, you know, stuff called cellular reagents. This was Andy Ellington's group at the University of Texas Austin have published on this. We've also recently published. You can find the papers are listed there, so you'll get it on the slides. Sanchita Bhadra is the main postdoc. Oh, it's going to go through it again. There we go. Is the main postdoc who's worked on that. So Sanchita's done some excellent work on also using cellular reagents in assays for SARS-CoV-2 and a number of other uses as well. But basically, they're really easy. You don't purify them. That's the thing. So you get your cells. In this case, we scraped it off the plates and we put it into a tube. You resuspend it in cold PBS, which is the standard buffer that most people have in the lab. You centrifuge it down. You wash it again with PBS. You resuspend it and you measure the absorbance at 600 nanometers. The standard optical density reading doesn't need a super fancy machine, but you do need some kind of way of testing optical density. And then you might want to dilute it quite a bit depending on how much you've got off of the plate. You note that if you're expressing red fluorescent protein, don't use optical density 600, use 700 because it interferes. So just a quick technical note there. And then basically, once you've got your optical density down to about 6 to 10, you prepare another 1 in 10 dilution, and then you calculate what gets you roughly 2 times 10 to the 8 cells, which I mean, I won't go through it. There's basically a rough calculation here that gives you give or take an amount, and then you pipette that volume into a 0.2 ml PCR tube. So this is just the cells. You haven't done anything to them. You've not lysed them. You've not done anything. You're just going to pipette them in their PBS buffer into the tubes. Sorry for the incomplete sentence there. It's because I moved the heat treatment onto a different slide, and I obviously did a bad job at removing that. But for example, if your final optical density 600 is 6.5, then you want 31 microliters of the bacterial suspension, so not a lot. And you actually don't want to put in much more than that into a single tube, because you'll see in the next step that we're going to dry it down. But before we dry it down, we may heat treat it. So this is cellular reagents. You haven't killed them is the takeaway. So it's fine if you're using it in your own lab. If you were planning to ship these anywhere, then do the heat treatment, because otherwise, technically speaking, you're shipping live GM organisms, and that is harder to do. So this is our test to see if they survived being desiccated completely, and they absolutely do. So ideally heat treat them at 60 for 10 minutes. This is fine for open vent because it's really robust, but for other enzymes that are not like high temperature DNA polymerases, it may be a bit more tricky. You may have to be more creative. Anyway, if you treat them, this slide just shows if you heat treat them for 60 for 10 minutes, they will not grow. So we've killed the bugs. And then we just dry them down. So label your tubes, obviously always label your tubes. And we put them in a piece of Tupperware. This is a glass kind of cooking dish, but you can use like a plastic lunchbox. Fill it with silica gel or another desiccant. Leave the lids open. In our case, we've also started using, you can buy vacuum Tupperware. I mean, you just get it off Amazon or kind of any other retailer. It may not be available everywhere, but where it is available, it's reasonably cheap. It has a little vacuum pump with it. And so we create a vacuum just to try and reduce some of the oxidation reactions that might be going on, but the vacuum is not necessary. It works without the vacuum. Place the Tupperware in the incubator at 37 degrees, and within 18 to 24 hours, you will have a dry sort of solution. You can just about see it here at the bottom of the tube. And then basically store it in a bag with a bit of desiccant. It should remain stable for 3 months at room temperature and 6 months at 4 degrees, and it works. You rehydrate it, you use it in your PCR reaction. There is a protocol that we'll link in the slides. It's a slightly different buffer to TACs and a slightly different PCR cycle, so don't just use it as a complete drop-in replacement to TAC, but effectively it works the same. I would mention 5 times higher fidelity, much more robust. You might be thinking, oh, but my work is too important. I cannot risk it on this unpurified enzyme. Well, we have good news for you is you don't have to. It works. Do not use it if your work involves the E. coli genome, because it's still got the E. coli genome in there. It will give you a whole bunch of weird results. You do get a lot of it. So 1 plate is thousands of PCR reactions. This is our SDS page gel showing expression here. Yeah, if you don't want to do that, obviously you can use whatever tag you put on it. So his tag, cellulose binding, whatever. I'm not going to go through that. But 2 other simple ways of just adding a bit of purification: heat treatment again. So if you want to purify it, you can lyse the cells in a lysis buffer, and then basically just heat them. And most other E. coli proteins are not stable at high temperatures. They basically precipitate out, and this is roughly what you'll see. And then you can see here you actually get quite a reasonably pure protein there that you can use. You can also use salting out with ammonium sulfate. So same deal, but you don't do, well, you can actually combine them. You could do the heating step and salting out. You basically lyse them, you add the ammonium sulfate slowly in solution, and then this is unfortunately not open vent because I decided to put these slides in very last minute, and then I couldn't remember where the open vent slide data was. But this is Clenau DNA polymerase, our old favorite. We were introduced to that earlier. And so you can see here, this is 40% ammonium sulfate, and it's pretty pure. I mean, it's looking quite good. You basically test a few percentages for each each protein to find out what works the best. And in this case, 40 is fairly effective. So again, you've got a much purer prep there if you feel like your technique is sensitive or for any other reason you want to use that. And that's pretty much the end. So that's open vent, how to express something. Every protein or enzyme in the collection is going to be different, and we have not tested all of them ourselves in terms of like different expression techniques or anything like that. You will need to search the literature for ideas, but if you do, we want to hear from you. So as Adrian mentioned earlier, we are very open to feedback. Tell us what we're doing wrong and what's making it difficult for you to use the collection, and we will try our best to fix it. You can join the Reclone forum, which is our community that's sharing protocols and sort of ideas. It's beyond the collection. There are other people who are sharing reagents through Reclone as well, but we're using it as our kind of primary forum and place to communicate, and that will get a bit busier in the new year as well as we start kind of adding more protocols. You can tell us what you want in the collection. So if you go to the Open Bioeconomy website, we have a submission form, or you can just email us and say, hey, I want this. We're planning to submit some more before the end of the year to get synthesized. So get on those keyboards quickly if you'd like to include that. It's not just enzymes. If you want reporters, tell us. We're really interested actually in like environmentally relevant kind of industrial enzymes. So we have some collaborators in Ethiopia that are interested in leather processing and proteases. So we're kind of having a conversation with them to select which ones to try. So get in touch. And that's it. Thank you very much. I apologize for going like 4 minutes over, but hopefully it's been useful. Maybe we have time for a couple of questions.
Yeah, absolutely. I think we have at least 5 minutes or more for questions. So if you guys have questions, just
Wonderful.
Raise your hand and we'll try our best to address them.
I will stop sharing. And yeah, just to say that if you are interested in kind of more contributing in a more concrete way, we are currently building out a small group of volunteers who are basically kind of corralling the open enzyme collection into better order and managing some of these new submissions that are coming in as well. So there's definitely space if people are interested to get more involved or just, you know, in any way collaborate. Adrian.
So you mentioned about the BSA one there. It's a part of the collection, which is fantastic. I'm really glad to know that. I know that though, I think I read somewhere that not all the BSA ones from the suppliers will work well with the Mowoh assembly. So my question is, have you ever, you know, ate your dog food? so have you tried the that one for the Mowoh assembly?
So the one we have is the same as our collaborator Santita Badra has successfully used to do assembly just using the cellular reagent version. So she expressed it with a methyltransferase, which the methyltransferase should be in the collection, but we've had a couple of issues with some of the methyltransferases and the restriction enzymes with Twist. So just in terms of synthesis, Twist is the company that we use for synthesis. And as with all DNA synthesis companies, there are some sequences they just struggle with. And so we're hoping in the next round of synthesis that we'll get through more of the methyltransferases and restriction enzymes. But yeah, you're right. I mean, so we do not have like the latest version 2 from NEB, for example. But the version that we do have is the same version that has been used successfully. It will of course be less efficient than the highly optimized NEB new version / new buffer system that they put in place. But no, it has been used successfully. I mean, there is only really one, there's one kind of wild type version of BSA1 that has been used. I think my understanding is also some of the problems are the buffer, not the enzyme. So I think there are certain buffer compositions that are way better for assembly. And that's another thing that NEB has really optimized, which is why their kits are so good compared to the kind of homebrew mixes. Yeah, it should work. As I say, the main problem is expression. But if I recall correctly, and I should know this, the methyltransferase is not in the collection at the present moment because we had the problems with synthesizing it, but it's on our list and it is going through, and that will, but just a kind of heads up that even if you have the methyltransferase, getting it they don't like it, the E. coli. They do not like this enzyme. So we've been working a bit harder on getting a cell-free. There's a paper out soon with a colleague and collaborator of ours where he's been using a crude cell-free extract to express BSA1 with good success. So that's another sort of route to go potentially.
In order to use it, we need to go to like a full chromatography, right? That's not going to work with the cell-free, sorry, not cell-free, cellular reagents.
Well, no, I mean, Sanchita got Golden Gate working with cellular reagents. I mean, she didn't do anything. She just,
okay.
Yeah, if you check her cellular reagents paper, you can see the methodology that she used. Yeah.
Oh,
so she had a plasmid with the methyltransferase and the BSA1. And so she had to do a lot of tweaking to get the E. coli happy enough to make enough of it. But yeah, she got it to work cellular reagents.
Oh, fantastic.
There are limits to cellular agents. We have found that they do work for LAMP, for example, but you're better off, the better the enzyme you can get for LAMP, the better the cellular reagents will work, because there does seem to be some sort of inhibition. We've also found limitations with cellular reagents, and for example, anything that's interacting with RNA. So Cas12, we have not got to work with cellular reagents. I mean, yeah, good luck with that. but yeah, for a surprising number of things, it actually is effective, which is surprising. I mean, I love it, because as a biologist, you just don't expect these things to work. So kudos to Sanchita for hard work on showing that it does.
Fantastic, thank you.
Okay, so just for everybody, this is Yuan Xue from Luna Landing, and she's going to be showing us how to make her own kombucha, but also tell us a little bit about the microbiology of kombucha.
Okay, awesome. So hi everyone, my name is Yuan, and this is you're looking at my kitchen in sunny California. So we're from a makerspace called Luna Landing, and I'm the founder of the makerspace, and we're relatively young. We started during the first time this year, but we still wanted to come and contribute to what we have with our students and bring what we learned to the community. So a little bit about myself. So I'm trained as a geneticist. So I work with a lot. I have actually never worked with kombucha and tea, but it's actually really easy. So I wanted to share my experience with you guys, so just so you can see how easy it is to make it your own voice issue. Okay.
It just breaks up a little bit. Maybe it's a bit quiet because you're far away from the microphone. Yeah, that sounds good. You can bring it back when you need it.
So right, so yeah, so I'm a microbiologist by training, but I have never really worked with kombucha. It's very easy model system to study microbial diversity and biochemistry, and a lot of cool stuff you can learn with it. And I believe like other makerspace have used it to study genomics as well. So we can touch a little bit on that as well. So so today is a little bit different. We're gonna do a live demo. I'm gonna use my own kitchen to show you how to do it. Unfortunately, you're not going to be able to make it because you need this thing called a mother or SCOBY to make your own kombucha. But you can follow along and and ask questions, and like it's gonna be a two-way discussion, and I'm happy to answer any questions. So first of all, I want to show you what it looks like. So this one, can you see? Yeah, so this one is like a SCOBY and kombucha culture. This is made 5 days. I started like on Tuesday night, and this is made by black tea. So we're basically fermenting the black tea using the SCOBY. And I'm just leaving it on my kitchen counter. It will be ready in about 10 days to drink. So today I'm going to use the SCOBY from this culture to make a new batch. And we're going to use not the traditional black tea, but we're going to use actually this thing. I think this is the hibiscus flower. We're going to use this. Let you see a little bit. So they're like dried flowers from like hibiscus. So they actually make really nice kombucha tea as well. So I really like this. So today we're gonna try to make this one. So, okay. Okay. So I don't know if you guys have looked at the folder. So I have uploaded a recipe in our common folder. So it has like the how to make a kombucha. It has a sheet of like all of the materials and what you need, and the protocols and the materials and basically where to buy the stuff. So if you guys are interested, you can have a look at that. So just a quick going through it. So to make the tea, we basically need a jar. And this is like half-gallon jar from Amazon, really cheap. We can get it, for like maybe $5-10. Then we have, you can see this. So we're going to have a cheesecloth. So this goes on top of the kombucha culture. Because it has holes, it will leave, airs going through. So the microbial will breathe and grow. And we have a rubber band to secure that on top. And then we also have some like tea bags so that we can, fill in your favorite type of tea and put it in. And I also include, including a tasting straw. So thank you. Yeah, thank you, Danny. So you can like put it in and actually taste your kombucha to see if it's ready. So during this, I will also taste it for you guys and see if it's good. Okay, so let's get started by like actually cleaning our vessels. So these, when it comes to our kitchen, it's not sterile, and because we wanted to grow bacteria and yeast culture in this, we want to make sure that we sterilize it and to get rid of existing microbials in it. So the first thing I do is to clean it. And there's many ways of doing it. I just doing by boiling water and run it through. And some people doing like really hot soapy water. And some people, do 1-to-1 dilution of distilled alcohol with water. So you can pick your favorite way. So I'm just gonna, fill in some water in the kitchen. You already seen, this is my pot. I'm going to just heat it up. So these are tap water, and they're just for sterilizing the vessel. So in this other pan, I'm going to fill like distilled water, or you can also get spring water. You can get like any kind of water. Filtered water is also okay. Just do not use tap water because it has chlorine and other stuff that's not very gonna give you a good taste in your kombucha. So I'm just going to get some water and get it boiled. Okay, so on the recipe, it's like 4 cups of water. But today I'm going to make a little bit less and reduce amount of like sugars and other materials accordingly. So you can like do scale up or scale down based on the recipe you get. So it's up to you. So I'm just gonna do 3 cups of water with the good water. Yeah, the reason I do less is because I have very small pans. So you can do more, or yeah. That's it. Okay, so everything's good, it's boiling. Okay, let's come back to this one. Yeah, any questions so far? You hear everything okay?
Mhm.
Okay, awesome.
People enjoy the double camera.
Yeah, I know. I have done this on Zoom many times, so it's like an Airbnb experience. Okay, so let me share my screen. Here.
Yuan, you do have one question. Nat asks, why the distilled water?
Why distilled water? Okay.
Over
Because
tap.
in California, unfortunately, we don't have a good water source. So we have chlorine and other treated chemicals for treating the water. So the taste of the water is not super great. And we don't want those chemicals to influence bacterial growth as well. So ideally, we wanted to, you know, very pure water, distilled water, mineral water. They taste better, and then you don't introduce any other, you know, unknown factors in your tea. So okay. All right. So today, let's go through some of the. Yeah, I'm going to sneak in some science here because since we're, you know, doing a live cooking show, we have some time. I'm waiting for the water to boil. So let's have a look at this. So do you guys know where the kombucha come from and what it is? Anybody guess?
No, I don't know.
Yeah, so what is kombucha? You can also type in the chat. Okay, I see. Bacteria, yeast, symbiote. Yeah, excellent. Some scientists here. Uses SCOBY. Great. Mushroom tea. Oh yeah, we can do mushroom tea. Great. Yeah. Okay, so so if you look, you know, online, you figure out that, you know, it's defined as a non-alcoholic or low alcoholic fermented tea. So it's basically tea going through a fermentation process. It produces 0.5% alcohol. But on the market, you will find that a lot of kombucha are so-called hard kombucha, so they have a lot of alcohol. I don't know how they get into that, but that's something that's very interesting, the fermentation process. So for many centuries, it's been brewed in China, Russia, Germany. So the origin of kombucha is relatively debated. But because I'm from China, I tend to think it is originated from China. And it is a symbiotic culture of bacteria and yeast. So that, you know, when you think about it, it's not just as a regular beverage, it's not just a drink, but it's also a living thing, right? So it has bacteria and yeast living in the system. You're drinking basically live culture. Okay, great. So anybody can identify the component in the picture? What's number 1, number 2, number 3? You can type in the chat. Okay, I see Jen says number 1, SCOBY. Great guess. Correct. What's number 2 and 3? Yeah, 3 is fermented tea. Great. What's the number 2? It looks like strands and stuff, you know, like threads going down. What's that? Anybody? Okay. All right, review the answer. Yeah, great. Yeah, so I see some correct answers. So the number 2 is actually the growing SCOBY. So when the SCOBY is growing, it actually produces the strands of like bacteria and cellulose matrix, and it's hunting down there. It's under like, you know, this massive cellulose matrix. So yeah, you sometimes see it. It's not obvious in all of the cultures, but it's quite often you can see it. So for example, in the current culture that we have, this one does not have the spread right now. And yeah. Okay. So what is a SCOBY? The SCOBY is a very interesting thing. So when we talk about it, you know, people are always very curious about this. It is, you know, we call it the mother or the, you know, there's many names to it. Basically, this is where you can grow your kombucha from. That's where your microbial diversity, your yeast and bacteria come from. So, biochemically, it is a cellulose membrane. So it is produced by the bacteria and has bacteria and yeast living inside of it. So we call it a biofilm. And we can find the biofilm in many, you know, scenarios. You can find it in like shipwrecks under the ocean. You can find it in space, in a space station. Actually, NASA is fighting for getting rid of the biofilms in their space station, because bacteria, they can form those protective structures. It blocks, you know, in other invaders from the air. You know, it protects from the UV light, from other, you know, other environmental insults. It basically makes a safety host for bacteria and yeast sometimes to live inside. So you can think about this as a floating cities. It's filled with microbes. Some other students told me like they think about this like, you know, like bacteria, yeast, and other viruses, and those microbes, they are holiday areas like Hawaii. You know, they're really happy in here. They live in a nice and happy community. They cooperate. You know, they make their own food. They're just happy together. So yeah, I think that you know, our water is boiled. So we're gonna go back and do some lab work and continue. Okay, so this is the tap water. So I'm going to use to cleaning the vessel. So this is boiled. I'm gonna turn the heat off and grabbing the jar in here. Yeah. Put this down the sink. Quickly. Yeah, basically I'm just gonna pour the water inside and on the outside of the vessel. This is my method, is very crude. And then I put the jars back on so to keep the temperature for a bit. And I just leave it there. And in a moment, I'll pour out the liquid, and then I'll let the jar dry by itself and cool to room temperature. So now we're having this this pan boiled, and this is going to be the distilled water for kombucha culture. So now what I'm gonna do is to add sugar to this, and then add the kombucha, the tea inside. So the sugar I'm using is this one. Yeah, you can see this one is just regular white table sugar. And later you will see why we're using this type of sugar. So on the recipe, it asks for, I think, for like 1/4 cups of sugar, but because we're using slightly less amount of water, I'll use a little bit less of the sugar. So I'm going to use a regular cup to measure it and just pour some sugar, and roughly, yeah, 1/4 or less than 1/4 of sugar in here. So, okay. So I'm gonna remove the heat. And pour the sugar inside. And I'm going to make sure all the sugars are inside. And you can stir it to dissolve it. It's very quickly dissolves because, you know, the water is really hot and we're not adding saturated amount of sugar. And then the next step is we're going to add tea to this. Today I'm using the flour instead of a regular tea. So you can see here, it's flour, and I'm going to fill the flour into the tea bag so it doesn't float everywhere. It's gonna be hard to fetch it later. So yeah, basically I'm putting the flours in teacups, tea bags in here. And this flour gives a really strong red color, so you'll see when it's dissolved. So this is very convenient. You just tighten it and it has a thread here. I'm going to fill 2 tea bags. If you're using regular tea, you can just using, this one is a black tea that I have. It's like Turkish black tea. It's very good. You can use any other teas, green tea, white tea. I will show you a slide what kind of tea you can use. So, but we're not using the tea today. We're using the flour. So I'm filling the other tea bag with flour. Now, good. Secure it, and then we're just dropping them in the pot. And yeah, I'm going to use a spatula and just to press it gently. So you see it's very red. It's going to make the whole culture red, but that's okay. So
Oh, we can't see that well. It's like at the very bottom of the screen. Yes. Oh, that's much better.
yeah, is it better? So if I press it, you can see it stains all the color red. So I'm going to leave it to steam for about 10 minutes. So yeah, someone can keep a timer. So that's it. Yeah. Okay, go back to the slide.
Stop your screen share, so you'll have to start it again.
Okay. Okay, great. Yeah. So now we're basically waiting for the tea to steam, to brew, and then in the 10 minutes we continue. So these are the scobies we're talking about, right? So these are made of microbes living in the cellulose matrix. So if you actually take out the SCOBY and stretch it, it's actually very, very tough. It feels almost like a leather. So actually people use it as vegan leathers. They dry them and they stretch it and they produce leather purses or any other leather goods with it. So it is a like cruelty-free leather. It's a very interesting material. If you look under the microscope, you see many type of bacteria and yeast living inside. So here you see, like on the right is the cellulose matrix, and then there are bacteria yeast actually living inside of those, and on the outside there are free floating bacteria and yeast as well. The bacteria are the tiny ones, the tiny like rod-shaped ones, and yeast are the bigger balloon-shaped ones. And then if this is a student like who 3D printed this biofilm structure, so you can see it is really not a 2D structure. The bacteria can growing and can can escape out of the structure as well. So this is a living citic. This is really a 3D structure. So so many students come and they ask me or they think about like what makes kombucha taste so good, right? Like what are the chemistry have in the kombucha? What's happening when we have bacteria and yeast in there, and what do they do to make the kombucha taste the way it is? So So first, let me know, like, describe what does kombucha taste like. Type in the chat. What does kombucha taste like to you? Like, what's distinct that of kombucha? Fruity, yeah, fruity. Is it sweet? Is it sour? Is it bitter? Okay, kind of sour. I see. Sweet. Fresh. Oh, sizzle. Yeah. So what does the sizzle, fizzy mean? What does fizzy mean? Does it mean like bubbles, right? Vinegary. Yeah. Sour. Great. Yeah. So what we actually like have is like, this bubbly gassy. Yeah, that's great. It's great summary here. So now, like, from this picture, I kind of like, ask students to think about what makes this kombucha sweet, what makes the kombucha sour, and what are the ingredients that are the sour one, and who makes the bubbles. So if you look at this, you can see that we're using the table sugar, and the main component of the white table sugar is sucrose, right? And the sucrose actually get digested or cleaved by this enzyme called invertase that's produced by yeast. And the invertase cleaves sucrose and produces 1:1 ratio of glucose and fructose. And that feeds into the bacteria, and which produces other chemicals such as gluconic acid, acetic acid, and to make the flavor sour. The sweetness is still coming from the residue sugar, right? Vinegary, yeah. And then, so now tell me, like, who makes the bubbles? Is it the bacteria or the yeast making the bubbles? Yeah, Nat says yeast. Yeah, correct. Yeah, yeah. Sarah says yeast. Yeah, so the yeast does the fermentation, right? So what we're familiar with, the yeast make wine. So what's wine? Wine has ethanol inside, and we also make the bubbles. Like what the yeast also make bread, so it produces ethanol and bubbles. That's why the bread raises, right? So yeah, the yeast is producing the bubbles, and who's producing the scoby, the cellulose component? Who's making the cellulose, the scoby that's floating on top? Okay, Claudia says bacteria. Great guess. Yeah. Yeah, so the bacteria has this ingenious ability to produce this polymer structure, the cellulose, and it's almost like a leather, it has a great material use. Yeah, so yeah, in biotechnology companies, sometimes we want to harvest this amazing ability to make cellulose using bacteria, and by engineering bacteria to produce cellulose more efficiently. Yeah, that's good. Okay. So yeah, so when we actually look through this these different type of drinks on the market, there's so many kombucha drinks now, and if you look at their percentage of chemical components, you get surprised. I was really surprised when I look at this hard kombucha of 7% alcohol in it. I do not know how they're making high alcohol kombucha, and then there's kombucha has 0 sugar. So yeah, very interesting, fermentation process. If you have any guess how they're doing it, it's very cool to share it. So, all right. So I think we're gonna remove the tea. I think it's probably 10 minutes also. I'm gonna remove the Yeah. So now you can see it's getting really red. And yeah, we're just going to let this cool down to room temperature. And usually this is the longest time consuming step. So it takes about half an hour to cool. We're going to move this off the heat and just leave it outside. And I'm also going to pull out the water in the vessel and let the vessel cool down as well. Yep. Great. All right, so now we can actually look at the microorganisms living in the kombucha, like by electron microscopy. So can you guys have a guess what's in the pictures here? What's on the left, what's on the right, what's at the bottom? Type in the comments below. So what are these microbes under microscope? Bacteria, yeast, and virus. I guess your order is left, right, and bottom, right? So great. Yeah. Nice. Yeah. So yes, so the bacteria we're typically found in this culture are rod shaped. So they divide by like fission. And then the yeast we see in this culture are typically budding yeast. So you see there's a mother cell that looks like a balloon and it buds off a smaller cell and leaving a scar. So the brown parts on the mother cell is the budding side, actually. And you see sometimes one mother can give birth to many daughter cells and leaving many scars. So yeah, so we call this a budding yeast. And yeah, in the bottom, like we have phages, that phages basically bacteria attacking virus attacking bacteria. And this type of virus is helping to keep the balance between the amount of yeast and the amount of bacteria living in the ecosystem. So it's kind of, we cannot have too many yeast or too many bacteria, or otherwise we don't have a happy community together. So the virus is playing an important role to balance this. So if we actually look at the species or the genera of the bacteria and yeast, we know that by genome sequencing, that the bacteria are typically what we call acetic acid bacteria as a general genus, because they all produce acetic acid, and they are rod-shaped, they're gram-negative, obligate aerobes. So basically they need air. And then when we do the sequencing, when the researchers did the sequencing and publishing those papers, the dominant genera are the typically two bacteria families that are the dominant one. And then there are certain species that are more common than others. So basically we roughly know like what are the composition of those bacteria in here. And in yeast, we know also like these yeast, they are osmophilic. Osmophilic means philic means loving, osmo means like pressure. So these yeast can live in the area with high sugar and high acidic content, high osmotic pressure levels, and they can thrive in those environments. So by genome sequencing, again, we can identify the genera, and one of them are the budding yeast that we know of that are producing wine and bread that we're most familiar with. So yeah, but I have to say, like, not everything is known. Actually, the genome sequencing studies has been done only recently for kombucha. So there's many new research has to be done to fill in the gaps of our knowledge. And this is where many other community labs come in. I believe like BioCurious, they are offering a genome workshop that works with kombucha. You basically isolate individual colonies from kombucha culture and send it to sequence and to identify what species it is. And like a very, interesting and process, and everybody gets to learn about how to grow bacterial cultures and how to do sequencing. It's a very like enriching experience. So yeah, this is why I feel like kombucha offers many learning opportunities for makerspace. So okay, let's look at what are the food that the microbes need, right? So the first thing we feed the microbe is the tea. So like typically, the most common kombucha are made by black tea. So today I'm showing the Turkish tea that I just got on the market. And then I also tried, pu'er tea, which is a fermented Chinese tea. It also produces delicious kombucha. And some people love jasmine tea or oolong tea. And some people tried mulberry leaves, red tea, white tea, hibiscus, flower, coconut water, and herbs. So basically, you can try many things. It's really no right or wrong. So, and then the other food that we feed the kombucha is the sugar. So this is actually more critical or like more stringent. So the ones we use is sucrose. So if you look at the bottom of the slide is the structure of sucrose. You basically cleaving the structure and produce glucose and fructose by this enzyme invertase from yeast. And then if you give it a different type of sugar, this fermentation process doesn't happen like this. So it produces some interesting effect. So typically we use table sugar, cane sugar, brown sugar because it contains mainly sucrose. But people have experimented with coconut palm sugar. Molasses from a tree, the tree syrup. And they are kind of slow fermenters and they produce like sour taste. Others have tried like maple syrup or agar, and they just don't taste the same. But it doesn't hurt to try it. I would say just try it and see what you get. And the other thing that's interesting is like it's not recommended to use artificial sweeteners or high fructose corn syrup. Do you guys have a guess why? Sorry?
We have a question from Anam. She says, can we use strain of yeast and bacteria to make kombucha?
Yeah, that's an interesting question. I think we can, like, we have to like isolate some, use isolated yeast and bacteria from the original culture, and then they may be able to form the SCOBY structure. Because I haven't tried personally. I think it's possible, and I also know that some people on the internet were teaching to make kombucha without a SCOBY, but they must have found some way to recreate the SCOBY. So yeah, if you can do it, it's like really great because then I don't have to mail all the SCOBY to you for you to make a kombucha. So that's a great question. Yeah. So does the tea needs to be black? What's the purpose of the tea? Okay, so I read the tea creates a hospital environment. You understand it. Okay, the tea and the sugar are the carbon sources. So basically the food for the microbes to break down. If you just give the sugar, I don't think you'll make kombucha because kombucha is a fermented tea. So you need the tea in there. Then does it have to be black? No, it doesn't have to be. So as we have in the slide, if we go back, this one you can see, different type of tea can make kombucha. Green tea, black tea, red tea, fermented tea like pu'er, even like plant leaves, flowers, herbs can make kombucha. So it doesn't have to be tea. So, okay. Yeah, so let's answer those questions about why artificial sweeteners and high fructose corn syrup does not work in kombucha. Any guesses? So think about the chemical structure of the, the sucrose, and think about what is in the sweetener. What is the high function compound? Right, incorrect food source. Yeah, so they're not the same chemical structure. So the sweeteners, if you Google it, what is in artificial sweetener? They're not, they cannot be broken down into simple sugars like glucose and fructose. So the bacteria cannot utilize it in a way that they utilize sucrose. So, we're not gonna get the same flavor. Okay. I imagine artificial sweetener does provide sugar needed and produce mostly fructose missing the glucose. Exactly. Yeah, that's right. So the other thing that's interesting is that they do not recommend to use raw honey as a sugar source. Why? Another question for you. So who produces honey? Have you tried adding fruit? Yeah, we did, like on the later step. This in the secondary fermentation step. Right now we're doing the primary, like the first fermentation step. And afterwards we can do a flavoring step and adding fruit and, sometimes I add mint and watermelon and yeah. And what else I add? Like you can try. I try carrots. I try many things. You can do that. Exactly. So impurities in raw honey. Yeah. So honey has. So who produces honey? The bee. The honeybee produces honey, and it's like basically it contains the content from the honeybee, right? So it has bacteria inside it already. So the honey will introduce outside bacteria, and you kind of can compete with the bacteria in the culture. Yeah, they can be angry. How about long-term storage? I'll show you. Yeah, so that's why, like, they don't recommend raw honey, but in my experience, I would say, try everything and do not judge it until you actually did the experiment and taste it. Okay. So yeah, so for the long-term storage, I'll show you. Yeah. So basically, after you grow your kombucha culture, you can put your SCOBY, in a jar. Like you can just collect all your SCOBYs together and make a SCOBY hotel. So this is like what it looks like. It can just pile up like pancakes. You can just keep it on the counters, step, and for many months, they will not go bad. Yeah. So in our makerspace, so basically introduce this workshop in the summer as a summer workshop, like STEM workshop for high school students. So we did this for like a 2-day workshop. The first is like a day 1 Zoom class, just like what we're doing now. And it will be like me and some students, and we will prepare our own kombucha tea together. And before the class, I'll always like prepare them a kit. So it will have the jar, it will have like the cloth and the sugar, the tea, everything. So all they do is to put them together in their own kitchen. So basically this works really well. And, we were able to make tea, by the first try. So they were tasting it, they were working well. The students were tracking, how the kombucha were maturing every day, like using a simple pH strip. So I can also show you. Yeah. So basically you can get those like really cheap pH test strips, and you open them up, like they shows you what are the pH levels, and you can use this to test what are the pH level in your culture. And they should be acidic, and they should get more and more acidic over time. And then it kind of give you an idea like which day it will be, good to harvest. And the other signs we look for are like bubbles to form, and then the SCOBY usually in the beginning it can be sticking to the bottom, but after 5 days or more, it either float or it will generate a baby SCOBY on the top. So you have like thin layer of biofilm worms on the top. So how much time do we have left?
We have about 7 minutes.
7 minutes?
Yes.
Okay, yeah, good, great. Yeah, so in this case, we'll start to, packing down our SCOBY and then, doing the last step of assembling our culture. So right now, this is still a little bit warm. So ideally, you want it to cool down to room temperature. Like you can touch it and it will not burn your hand. So we're just going to pour down this into the jar, like all of the liquid. And then, obviously you can make much more liquid and to fill it up. And today I'm just making a little bit. Then, okay, so maybe I'll do it in that kitchen counter. Yeah, so the last step is basically just taking the SCOBY from the original jar and transfer this to the new jar. So to do this, you need to wash your hands really well because it has a lot of bacteria on it. So I'm going to wash my hands. Yeah, so one other thing is you don't want to use like antibacterial soap in any of the steps because it kills your microbes. So now I wash my hands are clean. I open the cloth and then I'm going to just fetch this this one. You can use it with a utensil or a fork or whatever, and then you're going to pick it up and transfer it to the other one. Yeah, as you can see, it's like really smooth. It's really like a leather. It's very tough material. And then, there's one step that's recommended is that after you transferred your SCOBY, you wanted to put some like original culture onto the top. So the original kombucha tea, you wanted to pour a little bit on the top. So that keeps the acidity correct and keeps the bacteria on the top of the SCOBY to make sure that there's no other bacteria growing, competing with your culture and contaminating your culture. So I'm going to put this back and then getting a new cloth and then secure it with the rubber band. So here you go. So you have a new kombucha culture with hibiscus this time. And we're gonna keep it on the kitchen counter for about 10 days and tasting it. Okay. So that's it. Okay. Yeah, so if we have more time or anything, we could go over more questions or
Yes, we can do that. We can take some questions. If anyone has any questions, you can ask. Okay, we have one question from Ned. He says, how do you avoid contamination, and can you recover your SCOBY from a contaminated culture?
I typically found it's very hard to contaminate it. As long as you keep it at the room temperature, you do not put in the fridge, you don't freeze it, the SCOBY is very resilient. So it has bacteria in it. You can keep this in this hotel at room temperature. Sometimes I even keep in the food processor bags, and they will last. And as long as you use like clean hands and clean your jars, it's very hard to contaminate it. Can you recover from contaminated one? I think it's possible. So you need to do some surgery. You need to use your knife and cut off the contaminated portion, rinse it with the water, and I would probably do like a first batch testing it, and then if it grows well, and transfer it to a new jar and use it. Do not use it for the first time. Don't drink it for the first time. But
Great. We have another question.
Like you don't use the whole SCOBY, you just cut part of the SCOBY and regrow a new SCOBY. It's possible.
We have another question. Does SCOBY needs a special storage, temperature, or humidity?
Temperature, yeah, like room temperature is good. Don't put in the fridge. Don't freeze it. Humidity, I would keep it with some culture inside. So there are some living bacteria and yeast inside. So don't let it dry.
All right. David say that he knows that there are some carbon dioxide in injected versions sold in Europe. Can you add it afterwards?
Oh, yeah. I see. Yeah. So you can do like 2 fermentation process. Today we're doing the first one. After 10 days, also when it's ready, you can do another fermentation with fruit, with like fruit juice and other flavors inside, and put them in bottles and with this really tight cap. And then you put that in the fridge. So it will start another round of fermentation at low temperature. That's when most of the carbon dioxide is produced. And it's because, the cap is preventing it from escaping. It will just accumulate. You're going to get more and more bubbles in that. So can you inject it? Maybe that's, you can also inject it in a different way.
Right. We have another question. Can SCOBY turn into leather?
Sorry? Oh, can it turn into leather? Absolutely, it can. People have dyed it. They have dried it. They have stretched it and dyed it and made it into purses. Many different things. So.
All right. We have a question from Sheng Kong. She says that how does coconut water ferment, and can we use it as a alternate to water?
Yeah, I see people using it on YouTube. So you can try it. Maybe the fermentation will be longer and the taste is different, but people have used it. And some people says no. So when you find those, it's always conflicting, but in my case, it's always try it first and make your own judgment.
And the last question from Ned: do you have experience with water kefir? Do they have the same needs for cultivation as SCOBY?
No, sorry, I have no idea what is water kefir. You'll have to educate me on that one. But yeah, I have used kefir. I have not cultured it, but yeah, I think it's probably different for kefir. It's different bacteria. ABA is still ABA, but less yeast probably. But I will have to look into it. Thanks.
All right, thank you so much, Selena. Let's keep the conversation going in the Slack. If you have any questions, you can ask if Selena is on the Slack.
Can I share like one more thing just before we go?
Yes, yes.
Share my screen. Okay. Is this work? Does this work? Sorry. Just share one more thing so that we can keep in touch. Yeah, so basically we did microscoping gram staining using Kombucha as a culture system. We can do really nice, beautiful microscopes. And this is our makerspace information. We also have our own Slack and Meetup. And yeah, so if you guys can follow us on Instagram, you can see, you know, some of the information we're providing or our website. And so yeah, this is the one, like, this is my information. So if you have more questions, you can email me. You can also find me on Instagram. And yeah, please just drop a line and say hi. Thank you.
Thank you so much.
Yeah. You're welcome.
Just before you go, we have one last question from Shinkan. When you add fruit for the fermentation, for the second round of fermentation, do you still need this SCOBY?
No, you don't need. What you do is you take the SCOBY into the hotel and then you transfer the liquid and you bottle them in different smaller bottles and you put fruit juice or sometimes like minced fruit inside and leave some rooms for the carbon dioxide to accumulate. Otherwise it might explode. So yeah, there we go. Like smaller bottles, no SCOBY, just liquid.
Thank you so much, Selena, for that great workshop.
Yeah. Thank you so much for having me. Yeah, it's great to share. All right, thanks. Thanks, everyone.
So I brought my own slides. I hope that's okay. Mostly because they're written in JavaScript, so I didn't really know how to export them to PowerPoint. So I'll just see if I can at least share my screen to start.
Let me stop my screen.
Okay, and we can open with your slide just so people know what's going on, and then we can switch to mine. But I want to see if it works first. Yes, it does. All right, enough of the big reveal. I'm going to pause sharing. Does that turn it off? No, it does not. I don't know how to stop sharing, actually. How do you do that?
There's a green stop button.
Okay, yep, I see it. There we go. All right. We've just did the video testing. Thanks for bearing with me. Awesome.
Thank you.
I can see myself on my second screen. That's a little weird. I have a second screen just to see how the presentation looks from your perspectives. Always good for debugging when I can tell if you guys can see what I'm doing or not.
You are privileged.
I suppose so. I mean, it's running on the oldest Windows potato you could ever see in a screen I found for free, like on the street. But yes, very lucky to have it.
Yeah. All right, everybody. So I am going to just introduce our next speaker. We have Tim from Noisebridge, USA, and he will be presenting his workshop on how to design DNA at scales in seconds.
All right, should I take it from here?
Yes, you can take it.
Thank you very much. All right, so I'll share my screen. So to give you a little point of order, I'm going to tell you a little bit myself, then I'm going to do a quick presentation, then get to a couple of easy examples about how you can design primers for cloning out all the CDSs of a organism and some other fun stuff, and then sort of take questions and hopefully finish this before my 30 minutes. Actually, I plan to do it before 30 minutes. I talk really fast, as you can probably tell already. So just a little bit about me. My name is Tim, pronouns he, him. I grew up in the New England area. Actually, I am the guy who incorporated Biowatt back in the day. I used to be their treasurer in Boston, out in Somerville. I moved over to San Francisco a couple years ago with my spouse, who is now a grad student here. And you know, I really got my start in a wet lab, going to Boss Lab and saying, hey, I need to learn stuff. And they were like, well, we wanted to design a class, but we don't have time. Can you do it? And that's pretty much how I learned. I had like 3 PhDs looking over my shoulder, you know, via Slack going, oh, that's how you do it. Yeah. And that was my intro to wet lab experience. Loved it. And then I started wanting to start designing DNA. And what I found was there weren't very many good tools to do it. Lots of $100 copy and paste editors, but nothing that I was really happy with. So I started building this towards the beginning of the pandemic, and now I can sort of segue into my actual slides. So 1 second while I get that out. And feel free to pipe up with any questions. I am more open to this being discussion than anything, because this is my first time doing this as a joint talk / workshop / whatever. So if there's anything that's going wrong, let me know. That'd be nice. All right, so here's my introductory slide. And as you can see, it's one of my favorite creatures, the flying spaghetti monster. And I have this fantasy of engineering flying seaweed, and this is sort of the, you know, a nod to that. And so I'm something of a mad biologist myself. You know, I like to dream of silly things and try to make it reality, but I often find that just the basic, not even lab equipment, but the informatics, the being able to get information that you need and then make changes to it is absurdly difficult for a field that should be very data intensive. And so people often say that SynBio software isn't that bad, but you look at GenBank, which is really old. You look at all the code available upon request and papers, all the abandonware, the no unit testing or documentation, the classic, it runs on my machine, and the mountain of spaghetti code makes it really, really, really hard to engineer organisms via code. Even for the companies like Benchling and Genius that I bet most of you or many of you use, or even people in the Edinburgh Genome Foundry, or what's the other name? You know, people that use BioPython. So this is actually a funny piece of code. Can someone guess what this does and who wrote it? Anyone? Please, someone in chat, anyone, just take a stab at what this does. I'll give you guys like 20 seconds because I only got 30 minutes total. And don't worry, this isn't my code. I didn't write this. You don't have to be afraid for the rest of the talk. It gets better. All right, well, I'm not seeing anything, so I'm going to give you guys to like the count of 5. I'll just reveal it. 1, 2, 3, 4, 5. Okay, so this is actually George Church's code that was published in Nature circa 2013. And what this code, I think, does is it's supposed to transform regular ASCII or hexadecimal characters into DNA encoding so that you can synthesize it as DNA to do DNA storage. And the way I found this actually was that during Ginkgo's IPO, Patrick Boyle shared that he had to figure out this code to turn their IPO docs into DNA as a sort of a fun little trinket. And he was just complaining about it. I was like, yo, dude, do you need someone to talk to? This looks pretty bad. I just shared this with him and they got a good laugh out of it. But this is not atypical and you can't really use this. So this is kind of like how the field works. And at this point, at some point I was kind of getting almost ready to leave synthetic biology. I was really discouraged with the set of tools. Everyone's saying standards, but there were no standards. None at all, like zero. So this story kind of starts from an engineering perspective, like a lot of SynBio engineering projects start is I got a call from Keone Gandel. And if you don't know who Keone is, he's probably been given like 2 talks already at the Bio Summit. He is someone who Drew Endy hired to run BioBricks and a bunch of other fun projects over at Stanford for a couple of years, and now he's spun off and done his own thing. But at the time, it was the beginning of the pandemic, and Keone was getting ready to move on from his job at Drew Endy's lab and do something else. And part of that was he needed to figure out a way to convert GenBank to JSON and back but there was no way to convert to JSON and convert GenBank to JSON and back again, without his BioPython script breaking. And I was like, what? You mean to tell me that the world's most common data interchange format, I mean, literally almost every application you use, every web page you use uses JSON, cannot be converted into GenBank and back, which GenBank is the most common annotated sequence format? That's insane. That's like, that's absolutely nuts. both have been around for at least 20, 30 years. And it turns out that, you know, all the things available just broke. So it turns out that GenBank is really, really hard to parse. It was designed by a group of, you know, a committee of PhDs in the deserts in New Mexico in 1978. It's like, you know, white space formatted. Is someone in their kitchen? Hold on. Can someone, if someone's in their kitchen, can they please mute themselves? So, oh, I think it's Yuan? Yeah. Okay. Well, anyways, 2 weeks later, I got this
Yuan
parser.
was actually presenting a workshop before in her kitchen.
Yeah. Now, is there any way that you can mute her? Just because I occasionally get distracted by the pots and pans. It's no. Oh, she figured it out. Cool. So yeah, this is, you know, this is like the first stab at what eventually became called poly, which is short for polymerase. And I wrote this parser that could essentially digest GenBank as JSON and spit it back out. And it was some esoteric stuff. I mean, at some point I was actually cursing, like, you know, these people, I couldn't even find who made it. Like there's no documentation on who came up with this. It's just sometime in New Mexico, someone did it. So wait, no one can do Symbio because no one can parse GenBank? Yeah, pretty much. And I was kind of concerned. So I started writing more. I started testing it more. Everything's super well tested. Even the examples in the documentations are test, which means the documentation never rots, because if the documentation doesn't work anymore, my like CI/CD process is called continuous integration and continuous development process. It will literally, a bot will literally yell at me and say, hey, this doesn't work anymore. You can't push this. So the documentation is always up to date, which is amazing, even for like each version. And so, yeah, I have a link here, but we're not going to go down that rabbit hole because I should really speed this up so we can get the actual code. So now you can write code so that everyone understands it. Everything's in a style called literate programming. No single literal variables or mangled one-liners. If you try to write as much code as you can in one line, I'm sorry, this is not the library for you. And this is what I see when I like look at single variables in code review. What is this? A variable for ants? Just because I can't read it. It's really hard to read and it's not helpful to yourself in the future. Something that Keone and a lot of the devs will tell you about polymerase is that they actually know what they wrote like 2 years later. Keone's always astounded that he can look at his code from 2 years ago and be, hey, I remember what I did there. It's really cool. And I know that I haven't actually shown you the repo yet. I just remembered I forgot to do that, but I formed a random gang of internet nerds. And they've done something that fancy institutions and startup unicorns couldn't. They made a super stable synthetic biology library that works at scale, and you know, ships to almost every operating system without problems. And here's the contributors. Of course, it's a little blurry. You can check them out on the GitHub page itself. And these are all the things it does, but I'll cover that in the talk later. Sorry, this is the second time I've ever given the talk about this. And how can you help? I'd like a donation, but you don't have to do that. You can also just contribute to Poly or use it in your projects. And let's just go right into it. So I'm going to switch screens really quick here. And this is a good time for questions if anyone has any. But otherwise, I'll just get right to it again. So wait, hold on. Actually, I can show you the repo just to start. So if you want to follow along while I'm doing this, how do I... Sorry, the funny thing is the longer you code, the less you're actually able to use a computer like a normal person. And that's currently my issue right now. Hold on. So coming back to this screen, sorry. Okay, so apparently I got out of this, but oh, here we go. Great. So this is actually something I want to share in chat. This is the code I literally just wrote this morning, and it should work. Actually, it does work. I know it works. So I'm going to share it in chat and you can all follow along with what I'm doing, and you can actually add comments in real time, which is super cool. Okay, now I'm not seeing the Zoom call. This is not cool. Okay, this is weird. Oh, because I'm screen sharing, right? So I have to stop the sharing. Session distance. I apologize profusely. Here you go. So here's the actual pull request that I'm going to be working with right now. You don't have to be super familiar with Git, but if you just want to follow along there, it's fine. And then, got to go back to sharing my screen and then just go to my editor here. So this is actually something that I worked on this morning because I realized there you know, there needed to be a few more examples. I can actually go through a lot of the tests too. But if I just jump right back into this repo, this is what Poly is. It's about, I would say 3,000 or 4,000 lines of code, and it covers stuff from checking to see how DNA works, cloning, specifically restriction enzyme and golden gate assembly cloning. There are some command line utilities for converting file formats or hashing sequences. We have a really cool sequence hashing function for all you computer science nerds out there that makes it easy to do lookup tables for plasmids, which is non-trivial. And then we have a bunch of parsers for GenBank, GFF, JSON, Uniprot, and a bunch of other stuff. We have some primer design tools, some random sequence generators, the hashing function I mentioned, DNA synthesis fixing, which is non-trivial. And actually, I think this may be the most stable open source version around, and some basic transformation stuff. So, here's our little spiel. See all the test coverage, what it does, yada, yada, yada. But if I jump back over to, now I'm getting the hang of this. Jump back over to my little editor here, you can see what I'm working with. And so this is a basic getting started example where I am taking a GFP DNA sequence here, and I'm optimizing it to be later inserted into this Bacillus subtilis strain I have right here. B sub is what we're going to call it. So what I'm going to do, sorry, I have like a salt tab in my mouth. It's really awkward. As I'm actually going to debug this test and show you, step by step how it runs. And so we're going to wait for a second for it to load up B sub because it's a really large genome actually. Actually, wait, no, it's, so I'm actually, sorry. I need to get the speaker bar here is in the way of my other things. Okay, here we go. How do I just get this out of the way? Here we go. Sorry, you can't see what I'm seeing here. So if I go to the next step here, it'll load B sub, as we can see in the side thing, and you have some meta information about it. What's the accession number? What's its definition? What's the version from GenBank? Where there's keywords, the organism itself, its source. You can see more about its locus, the references that come with it, and the sequence itself. There's a whole sequence string that just keeps going very far off to the right. I can pull it back, but you can see it just keeps going and going and going. And then you get into some of the interesting stuff like the features or the annotations that you'll see in a GenBank file. And so if we click on this first one, you can see name, source, attributes, GPK location, sequence location, where I'll tell you the start and end. This is for the whole sequence. As you can tell, the sequence is 4.2 megabases. There's no complementary, it's not circular. It gives you all those attributes just parsed in. And so now we have this DNA sequence we're just defining. And we go down a step. And so now we have our GFP DNA sequence and our B sub sequence loaded in. And the question is, does anyone here not know what codon optimization is? Should I stop and maybe I should just explain that. So essentially the deal is that certain organisms prefer certain codons, and actually it's certain ribosomes prefer certain codons. And the reason behind this is, just some sort of optimization over evolutionary time, but it turns out that you need to optimize codon expression for the organism you're going to have to work in. So, so that means that you have to take your DNA sequence, and the roughest, easiest way to do it is just literally count the frequency of codons and coding regions of your DNA here. Of your, your reference sequence, and make a frequency table from that and apply it to your DNA sequence in a somewhat stochastic manner. Stochastic means random. And so what happens next is that if we continue down the line here, we're getting our codon table. GenBank has this really weird definition, but all you need to know is that this is the codon table for bacteria. And then we go to coding regions, which I think we just skipped over. I don't know how that happened. Coding regions is, it's a big old long string of all the nucleotides and all the codons and all of the coding regions of this genome. So it's a lot of nucleotides. And actually, I think we can look at the length here. No, I don't want to figure that out. Actually, yeah, it doesn't work. So if we skip to the next thing here, we get our GFP translation. So we built this optimization table, and as you can see, it's just counting start codons, stop codons, and just looking at all the amino acids and the codons related to it. and the weight behind them. So this is how many times this codon occurs in the sequence. And so when we come back here, we're going to now have our GFP translation. We're going to be translating our GFP sequence from a DNA sequence representation, which is, it could be any old codon switched around, to the amino acid sequence, which is, there's no permutations of it that are valid. It's only the it's like the only one true sequence for this GFP. And then we feed that into our codon optimized sequence function, which we're going to take this GFP and throw into our optimization table and get this codon optimized sequence for B sub here. And then when we come down, we'll get this optimized translation. So what's happened is we've already optimized the string here, but since it's a stochastic process, we need to make sure that the sequence is valid. So what we do is we take this DNA optimized sequence, which is right here. You can see it. This is the A, T, C's, and G's that all are now optimized. You can see that they're a little bit different besides the capitalization from the original DNA sequence here. So they've changed a little bit. And this is going to make it easier for these inserts to be expressed in B sub versus whatever original organism they're from. And then you get this nice little amino acid sequence that just verifies that this is the thing that we want. And that's sort of like a basic workflow, a very simple no loop workflow here. And it helps. And if you wanted to, you could do stuff like optimize, thousands and thousands of genes to be expressed in B sub in seconds. And we're going to do something similar to that effect down here. So if you're all familiar with cloning out, CDS regions and genes, when you want to clone out a gene from somewhere, you design a forward and reverse primer, and those sort of, mark where it's going to be removing where it's going to be cloning out these, copying these pieces of DNA. And so in this example, what I've done is I've wrote a quick script to design primers for every coding region in the B sub genome. So what this means is that I'm actually designing a primer library that will, if you sent this to Twist, they could print it out, send it back to you, and you could use it to clone out every gene in the B sub genome and use those for whatever purposes you like. This is a very common procedure. I'm not sure why everyone's doing it, but they do. And so I can just really quickly just sort of give you a rundown of how this works. So again, like last time, all we do is genbank.read, and we read in the genbank from this file path. We create essentially a list or a list of reactions here that we're going to append to during this thing. And so for every feature, and remember all of these, actually, am I running this one? Let me run this actually. So one of the things I really love about Go and this language I'm using is that I write everything in tests. Hold on, I hope this catches. If not, I'll have to run it again really quick. Let's just see if it stops there. So this is a debugger. I don't know how many of you are software developers, but essentially I can just go line by line and just check things out. So now again, we have our B sub. It's going to take a second to load because it's a big file. And again, we have our sequence, our features. We have over 9,000 features in this genome, which means that we're going to have to make 18,000 primers. Wait, no, sorry, that's just features, not CDSs. We're going to find out what CDSs are in a second. I think it's about 4,000. And so we are going to design 4,000 forward and reverse primer pairs in about a second. But just to give you an idea of how it works, we're going to do through the first iteration of the loop here. And so for each feature in this loop, we are going to check to see if it's CDS. In this case, it's probably not, it's a source, okay. And I guess I could, if we wanted to, just keep doing this. So I could just hit play, see if it comes out to, if it's a CDS, or actually the fastest way of doing this is just to hit play and go where it's already triggered if it's a CDS. So now we're on a CDS, which is a coding region, which means it codes for a protein. And now what it's going to do is it's going to step through, pick out the actual feature, the metadata here. So when I'm talking about a feature, I'm talking about this stuff, the name, the source, the CDS, the attributes, the location in the original genome, all of this fun stuff. And there may not be much, but at least it'll give us the parent sequence too. And then we're going to use this method that actually strips the, not strips, but copies out the CDS sequence from the large sequence that its parent sequence is. So now we have at this point, we should have a reaction.sequence. Sorry, this is a lot. This is my first time running this. And now we have, our CDS, again, what we've already had. We have our sequence for this particular reaction. And then we have our forward and reverse primers that we've just generated here. And then we append them to our, as you see, we're loading it into the object right here. And now we have with this reaction, we have our coding regions meta information, its sequence, and its forward and reverse primers. And when you run that, all the way through, which we're going to do now, we're just going to skip to the end because it's going to do about 4,000 of these. We're just going to hit play. And I can't believe this is working live. Live demos never work, by the way. This is a miracle to me. So we have, like I said, roughly 4,000 reactions, actually. We have 4,325 reactions. And they are simply all CDSs with forward and reverse primers. And as you can tell, they're all different forward and reverse primers of differing lengths, actually. And these all come from this nice standard function we have called PCR.designPrimers, which gives you forward and reverse primers given, the sequence you want to clone out and the melting temperature in Celsius that you want. And so now you have this large struct that you can export the JSON, you can turn it into plain text, and you can send it in whatever format you want to whatever DNA vendor you want. And, you've just designed 4,000 primers in less than a couple of seconds, which is why I said design DNA at scale in seconds. And even though this is, probably something you can do with Genius or Benchling, I'm not really sure. I don't really use GUIs, to be quite honest. It's just to sort of give you an idea of what's capable of this library and why I wrote it. And now I think I'd like to stop and ask questions and encourage people to do comments in chat and just hear what you all have to say.
Thank you so much, Tim, for the amazing workshop. If anyone has any questions, yes, Tim.
Hey, Tim.
Hey, what's up, Tim? I thought you were saying that I should be asking questions, but yeah, what's up, Tim?
It's the classic meeting of Tims.
Yeah, we have time. If you guys don't know, Tim and I know each other.
Very cool. Super applaud you doing a live demo. I would never. I would be too scared. And so I think it's a real testament to the technology that it worked well, right? To me, I'm looking at, I can totally imagine using it as like a command line tool. Can you talk a little about integrations? I know, I think I've heard from you that like people are using it in their like larger stacks. Can you talk about how it can kind of integrate?
So yeah, so the way that I would like people to use it is I'm sort of, a lot of people use Python. A lot of people ask me, why not do this in Python, right? And Python's a great language to learn. It's a great first language, and it's great for running stuff on your machine. But when it comes to running stuff on other people's machines, you may have experienced, trying to use someone else's code and they didn't remember the requirements.txt and they didn't do this, that, and the other thing. And Go kind of solves that. And that's kind of why I chose the language. And the way this integrates with other people is there's a couple ways this can happen. First, you can just write in Go, which is what I honestly just suggest. And there are people that are doing this. Enzymes is a great example. They got a gold medal at iGEM, writing all of their stuff using Poly, which was awesome to watch. I was actually a judge in the same track, and I don't know why they let me do that, but I didn't judge them, so it's fine. No conflict of interest there. Sure, why not? I did state that conflict of interest before I announced it. And so, Enzymes is using it just in the pure, we need to do it and Go. And I've noticed a lot of biotech companies are also, they're saying, wait a minute, our code's breaking all the time. Why is it all in Python? This is hard. We don't understand Docker. And with Poly, it just kind of just runs on your machine. We compile to, I think, 14 different compilation targets, like over several operating systems, package managers, and architectures. Like we run on M1 Max, which apparently our Bioconductor doesn't run on. So we are more portable than Bioconductor right now, if all of you want to know. And so the way that people are usually doing this and the way I encourage them is to write it in Go, just because Go is really easy to learn. It takes like a day. Like it took me almost no time at all. And if you want to do it via command line or something else, I suggest just writing an API. I mean, that's what I'm kind of going towards or leaning towards at some point is, you know, just write a JSON API. Maybe people will use it. I'm kind of waiting for someone to say, hey, I really need an API, Tim. Can I give you money for this? And no one's done it yet. So I haven't written it yet because I don't need it personally. So if all of you want to know, this is actually a completely open source project. It's MAT licensed all the way through down to the bone. You can do anything you want with it as long as you don't sue me. And, you know, there's no warranty. So also, like, you know, if you somehow set your computer on fire using my code, it's not my fault. You can't blame me for that one. Yeah, so the way people are mostly doing it is just writing it in Go though. But I can see the JSON interop. So we do have a JSON file format. And GenBank is really hard to parse. And I think there's only parsers in like a handful of languages. So if you want to write something in Lua using a GenBank file, it doesn't work. You have to write a parser by hand like I did for 2 weeks just to get your data. So what you can do with this is actually, we only ship 2 tools of our command line utility. One is a hashing function, which you can use to make super unique identifiers that you can, you can actually use for fast plasmid sequence lookup. And the other one's JSON to GenBank / GFF / all our random sequence file formats. You know, just a sort of interchange thing to JSON, because it makes regular web developers really happy. I can't tell you how many, what are you going to say to a web developer? It's like, hey, parse this GenBank file from 1970. They don't know how to do that. They make stuff go. So that's sort of how the interop works now. And, I'm working with some other stuff. I'm actually making a WebAssembly compilation target so people can just do it purely on the front end, which would be kind of cool, but that's for my own purposes. I've discovered that Go has a runnable playground environment you can use for all of my, for all the documentation tests I've mentioned. And those, apparently they have such an isolated environment that they won't let me put files in there. So a lot of the IO stuff just doesn't work. So now I'm writing my own front end environment for that. And that's sort of the thing is it's very portable. And I'm kind of hoping that people port what they want. And I've made it really easy to do that. I hope that's not too winding answer to your question, Tim.
No, I appreciate it.
Yeah.
All right. If you have any questions, you can just ask, or you can also write it in the chat.
I'll also put my Twitter here so you all can find me. And you can just DM me if you have any questions. It's the easiest way to get me. That's not email. Let's see. Hold on. I'm just about to DM one person instead of everyone. And there it is. If you'd like to talk to me, thanks. Thanks, Peter, for the beard compliment. I just became a shut-in during the pandemic and never stopped. This is like my third appearance on video. Everything else has been audio calls, I promise. No one's ever seen this before. All right. All right, everyone. Thanks so much for attending my talk. Let me know what you think and talk to y'all later.
Thank you so much, Tim. Everyone, we have another workshop right after this one, so don't go anywhere.
There we go. That's my volume button. How's everybody holding up in this room?
Amazing.
Just making sure I was on the wrong. Great. Connection. So I did have a moment here where I was really confused, and it's because the Open Innovation track was talking, somebody was talking about poly and Enzyme in there, and then Tim was talking about poly here. And I had them in both ears, and it was really confusing me for a good 5
everywhere,
minutes.
Maria. I don't stop. I bet you Isaac pitched us really well, actually. The Enzymes team used us to use my software to get gold. I mean, they did a whole bunch of stuff. They even added.
They did, and they were talking about their use of poly in the Open Technologies track while you were talking about poly here, and it was just one of those convergence moments that cracked me up a lot. And only I was in on the joke, so I felt a little bad. So.
Well, that means that I got everyone at the same time. I've covered like what, 2 out of 4 tracks? Yeah, there we go. Everyone knows. I'm super excited about Friendzymes too. They've done such a great job at iGEM. I was a little bummed that they didn't medal, but I don't. After judging, it's all subjective. Besides just the checklists. It's just
you know what? We know that they're the best.
Oh yeah, no, they've been great. I think Isaac recruited like half of Friendzymes from my Discord actually, and that's part of why they're so forward on this. So yeah.
Oh, that's how you take over. That's how you do things. But I had to share that anecdote with you because it was really making me crack up after I decided I was not actually hallucinating.
Oh, God, I'll go look at the recording. I would hallucinate too. Every time I see Isaac talk about my work, I'm like, wait a minute, that's me. And I'm not talking about it. What's going on here?
Actually, I don't even know if it was it. I don't even remember if it was Isaac. It might have been. Was it Isaac? I don't know who was talking. We had Friendzymes in like 3 different presentations talking about 3 aspects of the project.
They're so busy. I just I just do my 1 presentation at conference, maybe 2, and they'll take over entire segments if you let them.
We are aware. They are everywhere right now.
Yeah. Oh, are we ready for the next? Is the break over? Are we ready for the next?
Yes, we have. Since this is the wrap-up session.
Oh, all right. Well, I'll yield the mic to Benno. Excuse me.
Thank you.
Hi, friends.
Hello, Benno. So we have Benno from Floating Fab Lab team, and he will be presenting on how to design an eco biolab.
Wonderful. Thank you so much, friends. I am super happy to share these experiences with you. Here I am in Peru. It's part of the Amazon rainforest. I grew up here in this very amazing big biolab. And also during my life, I met another labs, like Fab Labs, 10 years ago. Part of my motivation to how to design an eco-biolab is this challenge. How could we empower with digital tools our biodiversity? We are losing biodiversity, and especially in this context in the Amazon rainforest, we are in more than 25% of the biodiversity in this rainforest has been lost. So how could we change that? How could we understand this territory? So this introduction to the workshop will be to have some key points if you want also to design an eco-biolab, and I will take as a reference the floating Fab Lab that we are developing in the Amazon rainforest. First step is to understand our territory, where we are. In the case of the Amazon rainforest, it's a liquid territory. It's a space that moves, and people are moving and living in the moving. So that's the reason why we decided to create a floating lab that will navigate the Amazon and also open opportunities for local communities. This is extremely important for us because we don't want to just to put technologies, just to bring machines or labs. We want to make this together. We want to understand and interact with the local communities and nature and generate a new lab. So this is part of the knowledge that we could incorporate to the structure or the design of our biolabs. So this biolab, it's also playing it to disassemble in order to bring more opportunities to different communities in the complexity of the network of rivers that we have in the Amazon rainforest. So this is part, the first step is to understand the territory, and this territory today is very complex because I mean the actions of people on this territory are not connected with the life cycle of the regenerative process that nature have. So what we are doing today is taking out a lot of resources from the Amazon and giving back contamination and predation and massive extinctions of species. So one of the main questions that we have is how could we change this flow in order to take not the material, not the matter, or not the physical resources, but the biological data, the biological information that we have in our biodiversity, and reinvest energy and different sources in order to increase our biodiversity. How could we invest in biodiversity in the Amazon? It's part of the regenerative economy that we want to promote in this landscape. We can find some recent researches about this concept of regenerative economy. One of the most recent is that published the last year by the European Union. I recommend you can search more about that if you are interested in that. So going to the Amazon, if you have been in the Amazon, please, I would love to know it. Maybe you could write in the chat, please, if you have been in the Amazon rainforest. Well, let me show you a little bit about this characteristic of the Amazon territory. So when we are in the Amazon, it's, as I said, a territory in movement. I will change my desktop. Yeah, here we go. Okay, so the first step to understand the Amazon, it's what are the forces that regulate all this ecosystem. And the main forces are the rain. The level of the rain changed everything. No? You can see here the level of the rivers will grow up more than 6 or 7 meters per station. That means you will have like an amphibian territory. Part of the year it's on the ground and part of the year is on the water. No? So it means the territory of the Amazon is moving in vertical, but also it's a territory that are moving in horizontal. This is a fast movie of the Amazon River and how it will changing during the last 30 years. No? It moved, and one of the main cities in Peru at the beginning were located close to the river, but right now the river cross so far from the main ports of this city. So one interesting thing is how the local communities understand the environment and how could we learn from these local communities in order to create more sensible strategies to adapt to the context. Before the traditional or modern cities, the local communities don't stay too much time in one place. They move in a territory, bringing the possibility to nature to self-regenerate. No? They have like a cycle that could, it could take like 3 or 4 years. It depends of the region, but in between 3 or 4 years or 6 or 7 years to give a cycle. No? But this is a process to be connected with the local cycle, with nature, and then self-regenerate. No? But what is happening today, it's a more centralized system that takes resources and don't give back the opportunity to nature to self-regenerate. No? So how could we create a strategy in the territory that could be more connected with the local cycles? So this is another very important key part in the design of an ecolab. What are the local cycles of the different resources that we have? What are the frequency of, the frequency of regeneration of the different materials that we are going to use in our lab. So this knowledge for local communities is very clear. No? They know that they cannot take too much of palms, or trees, or another resources in order to generate, as we are going to see in few minutes, the different houses model that they have. No? So this is first part of introduction, just to understand how, in this case, this ecosystem works and how could I connect my EcoBiolab with these different cycles. No? What's interesting, as I said before, it's in the case of the Amazon, it's a very dramatic difference in between one station and the others. That's the reason why local communities have to create many different strategies for housing, for example, no, in the highlands, in the floating houses, or on the pilots. Okay, so I will come back to the PPT. Okay. So we have different strategies for housing, in the fixes or the highland, on the rivers, the floating houses, on pilots. So the first part to understand this ecosystem was to create, was also to research how nature could adapt or have been adapted to this different situation. For example, in the case of housing, one amazing response or reaction or adaptation of the local trees, it's the pambil. Pambil is knowledge that the walking tree. Can you imagine that? It's a tree that can move in 10 years, maybe 6 or 7 meters. And the reason it's because the roots of the plants grew up outside of the ground, because I say you the ground is very unstable because the water level. So this is a strategy that the plant have developed in order to self-equilibrate, where the plant feels more inclination, it will grow more roots in this direction. So all this knowledge has been part of the research that we had in the local system. For example, the properties of ayahuasca, not only the hallucinogenous. Sorry, this word I don't remember. But not only the visualization that the ayahuasca brings you, also the structure that it have is very interesting to understand the flexible and self-regenerative system. It have many different layers. So with all this knowledge, we started to create some prototypes in understanding how nature has been adapted to this territory. We designed it and made these different modules using digital technologies and local materials and local knowledge. But at the end of this adventure, we understand that nature doesn't print objects. Nature grows, nature evolves, nature self-repairs itself. So how could we don't 3D print something? How could we design structures that could grow, that could self-regenerate, and also could develop new materials and be connected with the local cycles? This is part of our challenge today, how to jump from the digital fabrication challenge to the bio opportunities. In this sense, I also would like to share with you some strategies that ancient knowledge from local communities have developed. For example, in this case, it's not in the Amazon. This is in the Titicacas Lake, is the Uros Island in between Bolivia and Peru. These are the islands, and as you can see, and what is interesting of this strategy, these communities make everything with just one material, with the totora. This totora, I don't remember the word in English, sorry if you can help me, please, that would be great. They made everything with this single material. They made the islands, they made house, they made the system of transport, the furniture, many different things. And what's interesting, it's when, I don't know, it could take 2 or 3 years after this time, the totora will biodegrade and come back to the lake and grow up again. So we have a almost closed system to make everything with that. And also we have this other very interesting structure developed by the Incas culture. It's Morai, it's the agro lab of Incas, where according with John Earth, you can also search this very, very interesting book that show us how Incas create strategies to adapt it to the context, but also to explore. This is like a biolab for biodiversity, because they explore what characteristics they need, for example, to grow corn in order to grow in different ecosystems. And the reason is because in this structure that have not more than 200 meters of altitude, they have concentrated more than 2,000 meters of ecosystems. So according with that, they could explore, they could experiment, they could see what are the variables that they need to grow some species in another context, and then they scale that in the territory. So this is part of our challenge. How could we take local resources And in this case, in the case of the Florin lab, it's, for example, the microalgae that grow in the Amazon River, and how could we make biopolymers in order to print the facade and then to give back to the river and bioregenerate with that. No? So, well, these are part of the exploration that we run with a team. This is a team that is located in different parts of the world. And also part of the challenge is how to create like an artificial gland, no? That we could control some characteristics of the facade and the growing of the microalgae on the facade. This is part of the exploration that we ran during the Bioacademy, the first Bioacademy in 2015. And how could we create biocircuits in order to control the characteristic of different materials? And also, how could we control the growing or the movement of microorganisms according to different stimulus? So we make this growing machine for coffee fungi and explore with galvanotaxis and measuring how many volts do we need in order to stimulate, for example, horizontal or vertical growing with these microorganisms. And also in more theoretical exploration, how could we hack some bacteria to control the movement of the bacteria according to red light or ultra UV light, etc. No? In order to also send some data to the structure and control the growing in some directions of the Biolab. So these are part of our explorations. In short, how could we explore the characteristics of the ecosystem, of the environment where we are, and then how could we create growing structures and exploring the different materials. We are developing that for the Amazon, but we believe that we could replicate that in any part of the world according to the characteristics that you have in your local environment. In this sense, I would love to share with you a platform where we would like to invite you to join. You are interested to explore. Let me. Okay. It will be great to join efforts and to explore adaptations of these systems according to your local environment. I will paste here. Okay, please join this link. We are going to come to this interface. This is a platform that we have developed. It's in BioCreation. It's our platform for collaborative creation. No? So here we have the 3 areas. If you are interested to join this community and also to, I don't know, maybe if you have some research in these areas, that will be great to know it. If not, but you want to know and you want to be part of this this process, it will be great to join the efforts. So it's very simple. You come to the link and you will see at the top of the interface, participar. Sorry, it's in English. Sorry, it's in Spanish right now, but well, I think it's easy to understand. You could press the button participar and you will join. So we are going to wait for you, and we will open this space for your questions, comments, please. Visiting the Amazon, it's in my life to-do list. Excellent. Excellent, Mike. Not yet. Nat Rodriguez, we wait for you. Yeah, as I said, well, we are developing that for the Amazon, but we would love to work together in any context that you are. That will be great. We are using the galvanotaxis to, let me show you. Okay, our goal is to generate controlled structures, to control the growing of some structures inducing some stimulus. To make that, we started to explore, well, how could we control the growing of bacteria with light, with chemical, putting some, I don't know, depends of the microorganism that you want to use, and well, we explore with many different chemical attractions with some nutrients or maybe with some poison, and you can control, but in a controlled interfaces, in horizontal first, and then we, like a 3D printer, we add another layer and then another stimulus. But in the case of this galvanotaxis, yeah, this is interesting if you want to explore more in this how to grow, how to control movement or growing of different species. Yeah, you can use many different stimulus. It depends of the microorganisms that you want to use. In this case, is the fungi. The fungi we could control the growing, not the movement. But of course, you are exploring with, I don't know, E. coli or another that could move. Yeah, you can also maybe create structures more faster than this. So in this case, we had different space of exploration with different balls and the same quantity of coffee fungi inside. And also we have different mediums. Yeah. Then in our first exploration, we just release the fungi to grow, to measure the speed, the area, the density, etc. And then with the other capsules, we started to explore what happened is, well, here we have one example, well, we have another example where we create many other geometries according to the voltage distribution. In this case, both have the same time of growing, but these fungi grow more in vertical, very concentrated, than the other more in horizontal. So we want to explore that with in more deepless way. This is part of this research of how to grow an eco-biolab. But grow these microorganisms in the facade of, in this case, of the flooring fab lab. Yeah. So if you want to explore more in this, oh, Dani is here. Welcome, Dani. Welcome, Juan Fiore. Maybe more people. Thank you to join. Please, I will. I think it's in the, yeah, Gibson Biolabs. Welcome. Thank you to join. Okay. Yeah, please join the link. What's the idea? It's to, if you want to, for example, to explore more or contribute in one of these three main things, territory or modular structure or more material exploration, you could join with that. So how could you join one of these bubbles? For example, in this case, Naomi, welcome Naomi, Salim. Here I am, right? So I click, right click here, and then I will choose my group, for example, territory, and I will change. You could create another one. You could create more bubbles if you want to participate in more than one group. In this case, here I am again. And I could join, for example, here to other. And that's the way to join more than one group. Okay, my friends, I hope you could join and we could, well, the goal is, we understand this is a very short workshop. It is more like an introduction and more like an invitation if you want to continue developing that. Our goal is to make some structures, distributed structures together, and make it real in different contexts. No? If you are, I don't know, no? In rural areas, great. If you are in urban areas, of course, great. We could apply the same principles and replicate these control structures in different levels, no? According to the environment and the regenerative cycles of some materials, and then how could you create this process in controlled environment also, and then what kind of micro species could you grow in your structure, and then how could you control the different variables of these species in order to control also some properties that will be important for you. So we are not doing that alone, of course. We have a group, and here in the room we have two, I can see Super Delia and Super Fiorella. Maybe you want to say hello. Hola, hola, Delia Fio.
Hello to everyone. I am Fiorella. Nice to meet you guys. I hope you can join to the Bio Summit and with Beno Juarez, who is an amazing, amazing person and a great innovator.
This is not part of the plan, but thank you, Fio. Thank you, Fio. We have here also to Diana, Didi, Super Didi is part of the team too, of this exploration.
Thank you, Fiorella. We have a question. Have you considered trying to control the silica skeleton produced by radiations?
Nice challenge. I have not considered it, but it will be great to explore. If you want to explore Super Minette, count me in. But it sounds very interesting. Yeah, that's amazing challenge, and we are aligned with this exploration. Thank you, Scott. Some comments. Is anybody here, I don't know, exploring like grow structure, controlling, growing, or yeah, part of this, a lot of, I'm sorry, I will share my desktop again. All these explorations we started in the Bio Summit, sorry, in the Bio Academy with Super David, George Charles, etc. And we hope also to continue developing that. I have a question for David is here, no? Super David, when are we going to restart the Bio Academy globally? Please tell us the good news. Super David, are you here? Oh no, saying it's not. Or he's in many parts, in many, everywhere.
His microphone may be not working.
It's true. Yes, yes. Well, okay, friends, let me go back to here. Okay. Yeah, thank you, Salim. Yeah, if you want to, thank you, Gibson Biolabs. Also Betty, Naomi, Fio, Danny. If you want to add information or maybe your contact or some ideas, you can register here. And if you want to create more bubbles, you can explore all these buttons, and you can create more levels of these of these bubbles, no? Just to show you what kind of workshop we run with this. Yeah, we start like small groups of bubbles, but then we could, for example, it was the last week in Santa Cruz in Bolivia, creating a workshop with 250 guys, joining effort with different ideas it is a convergence of proposals and ideas. Now, this is exactly what we are starting today with you. And we want to invite more people to join and create together and co-create in different ways. No? So we start with individual proposals, individual ideas, and then we join and create groups according to the interests of the people. And at the end, we prototype or make one idea that take the best of all the proposals. No? So this is the SynBio creation process, and you are invited to run this, to continue the workshop after the BioSummit.